Good evening and welcome to Physic for Sleep. Tonight we embark on an intellectual journey into the heart of quantum mechanics, exploring its most profound mysteries. The quantum paradoxes, unraveling the peculiar tales of Schrödinger's cat, and the intricate dance of entanglement. Before we gently immerse ourselves in these mind-bending concepts, I would like to know where you are at this moment. Perhaps you are nestled beneath a warm blanket, listening to the soft hum of the night, or gazing out from a quiet balcony as the city lights twinkle below. If these deep reflections help you relax and organize your thoughts before sleep, please support the channel with a like and subscribe so others can find their way here too. Now, just breathe, allow your eyes to grow heavy, and let's begin. The journey into quantum paradoxes often begins with a peculiar thought experiment, a mental image conjured by the brilliant physicist Erwin Schrödinger in 1935. He sought to highlight the unsettling implications of quantum theory when applied to the familiar macroscopic world we inhabit. Imagine, if you will, a sealed steel box. Inside this box, there is a cat, a living, breathing creature. Alongside it, a delicate apparatus, a single radioactive atom, a Geiger counter designed to detect its decay, a hammer and a vial of hydrocyanic acid, a potent poison. The radioactive atom is at the heart of this curious setup. According to quantum mechanics, such an atom does not simply exist in a definite state of having decayed or not decayed. Instead, until it is observed, it exists in a state of superposition, a blend of both possibilities. It is, in a profound quantum sense, both decayed and undecayed simultaneously. This is the fundamental strangeness of the quantum realm, where particles inhabit a probabilistic cloud of potential states rather than a single, fixed reality. Now, the apparatus is designed so that if the radioactive atom decays, the Geiger counter detects it. This detection triggers the hammer, which smashes the vial of poison. The poison is then released, and the cat, tragically, perishes. If the atom does not decay, the vial remains intact, and the cat lives on, unharmed. The crucial point here is the linkage. A microscopic quantum event, the decay of a single atom, is tied directly to a macroscopic outcome, the fate of the cat. So the paradox arises. If the atom exists in a superposition of decayed and undecayed states, and the cat's fate is directly dependent on that atom, then what is the cat's state before anyone opens the box to look inside? According to the strict, unadorned interpretation of quantum mechanics, the cat too must exist in a superposition. It is, within the sealed confines of its box, simultaneously both alive and dead. Not one or the other, but a blurring of both realities, a ghostly existence in a quantum twilight zone. This idea, of course, is deeply counterintuitive. In our everyday experience, a cat is either alive or dead. There is no intermediate state. This is precisely the point Schrödinger was making. He found this implication absurd, arguing that quantum mechanics, as it was then formulated, seemed to break down when scaled up to everyday objects. He intended the thought experiment as a critique, a way to expose the measurement problem, the perplexing question of when and how a quantum superposition collapses into a single, definite reality. When does the universe decide the cat's fate? Is it when the atom decays, when the Geiger counter clicks, when the poison is released, or only when a conscious observer opens the box? For decades, this cat paradox has served as a touchstone for discussions about the nature of reality and the role of observation in quantum mechanics. Modern physics has offered insights, though the fundamental mystery remains. The concept of decoherence suggests that the interaction of a quantum system with its environment causes the superposition to effectively disappear, making it appear classical. In the cat's box, the quantum state of the atom quickly interacts with the Geiger counter, the hammer, the poison, and the very air within the box. These interactions cause the system to decohere, meaning the quantum possibilities essentially branch off, becoming increasingly separate and inaccessible to one another long before a human eye ever peeks inside. The cat, in this view, is never truly both alive and dead for any extended period, because its quantum state immediately interacts with the environment, forcing a classical outcome. Yet the initial quantum oddity, the potential for being both, is what the thought experiment so vividly illustrates. This enigma invites us to consider how our own reality is constructed. Are the choices we make, the paths we take, similarly in a state of superposition until some form of observation or interaction solidifies them into a singular experience? Perhaps just as the quantum cat embodies a duality, our own potential future exists as a tapestry of possibilities, each woven with threads of uncertainty, until the very act of living, of experiencing, collapses those waves into the tangible present. It is a profound thought, allowing us to see ourselves not as fixed entities, but as participants in an unfolding reality, shaped by the very act of our awareness. And so we move from the unsettling image of Schrödinger's cat to the very heart of the paradox it illuminates. The blurring of quantum possibilities, a principle known as superposition. At its core, superposition suggests that a quantum particle, before it is observed or measured, does not possess a definite state. Instead, it exists in a kind of fluid, indeterminate condition, simultaneously embodying all its potential states at once. It is not one or the other. It is a blend of every possibility, a spectral existence of what could be. Imagine a single electron. It has a property called spin, which when measured along a particular axis can be either up or down. In our everyday world, something is either one or the other. A coin, once flipped, is either heads or tails. But in the quantum realm, before we actually look, the electron is neither definitively spin up nor spin down. It is a superposition of both. It is as if the coin is perpetually spinning in the air, embodying both outcomes, until the very moment it lands and we see its face. This is not a trick of language or a limitation of our knowledge. It is, according to our most successful theories, the fundamental nature of reality at its smallest scales. The mathematical description of this strange quantum state is called the wave function. This isn't a physical wave in the ocean, nor a sound wave traveling through air. Rather, it is a wave of probability, a comprehensive map that describes all the possible states a quantum system could occupy and the likelihood of finding it in any one of them. Until a measurement is made, the wave function encompasses all these possibilities, a rich tapestry of potential realities. It is only when we interact with the system, when we seek to observe its properties, that this wave function collapses, forcing the system to shed its multitude of possibilities and settle into a single, definite state. This is the moment when the spinning coin truly lands, revealing either heads or tails, no longer a blur of both. This phenomenon, the collapse of the wave function, is perhaps the most debated and least understood aspect of quantum mechanics. What constitutes a measurement? Is it the act of a conscious observer? Or is it simply any interaction of the quantum system with a larger environment? Most physicists lean towards the latter, introducing the concept of decoherence. Decoherence suggests that the delicate superposition of quantum states is easily disrupted by interactions with the surrounding environment. Even the faintest touch of a stray photon or a random air molecule is enough to cause the quantum system to lose its coherence, effectively choosing a classical state long before a human observer becomes involved. So, for Schrödinger's cat, the quantum state of the radioactive atom quickly decoheres through its interaction with the Geiger counter, the hammer, the vial, and the very particles within the box. This interaction forces the system to commit to either decay or non-decay, meaning the cat observable duration. The quantum weirdness is confined to the microscopic realm, shielded from our macroscopic perceptions by the constant interactions of our warm, messy world. The transition from the quantum world of superposition to the classical world of definite outcomes is not abrupt, but rather a gradual process. Tiny particles, when isolated and undisturbed, can maintain their superposition for measurable periods. But as systems grow larger or as they interact more frequently with their environment, the effect of decoherence becomes overwhelming. The delicate quantum correlations are washed out, and the system behaves as we expect classical objects to behave, with definite properties existing in one state or another. This profound understanding reshapes our perception of reality. It tells us that the universe, at its most fundamental level, is not a collection of fixed, solid objects. Instead, it is a realm of probabilities and potentials, a dance of possibilities waiting to be actualized. When we reflect upon this, we might consider our own experiences. Are our thoughts, our decisions, our very sense of self, similarly emerging from a quantum substrate of unchosen possibilities? Does the act of conscious decision, in a metaphorical sense, collapse our own wave function, shaping our personal reality from the myriad paths that lay before us? It is a tranquil thought, suggesting that the universe is not merely observed, but in some deep, intricate way, actively shaped by the very fabric of its existence and by our subtle participation within it. As we gently drift from the concept of particles existing in multiple states at once, we arrive at perhaps the most profound and perplexing aspect of quantum mechanics, the moment when reality makes its choice. This is the realm of the measurement problem, a deep inquiry into how the fluid, probabilistic quantum world transforms into the definite, singular reality we experience. It is the question of what happens when the observer's whisper compels the universe to commit. For a quantum system in superposition, like the spin of an electron being both up and down simultaneously, or Schrödinger's cat being both alive and dead, this indeterminate state persists only until a measurement is performed. The act of measurement, of observation, seems to force the system to collapse into one definite outcome. The electron is suddenly either spin up or spin down, never both. The cat is definitively either alive or dead. But what exactly constitutes this measurement, and why does it have such a dramatic effect on reality? Early interpretations of quantum mechanics, particularly the Copenhagen interpretation championed by Niels Bohr and Werner Heisenberg, grappled with this. They posited that the act of observation, or more precisely, the interaction of a quantum system with a classical measuring device, is what triggers this collapse. It is not that the observer's consciousness is mystical or magical, but rather that any interaction that extracts information from the quantum system, linking it to the larger classical world, causes its delicate superposition to break. It's like trying to gently observe a fog bank. The very act of shining a light on it or moving through it changes its form. This transition from the quantum realm of possibilities to the classical realm of certainties is often explained through the concept of decoherence. Imagine a quiet, still pond, its surface smooth enough to reflect the sky. A tiny ripple, a quantum state, can exist on this surface for a moment, spread out and ethereal. But then, a drop of rain falls, or a breeze stirs the surface. The delicate ripple quickly interacts with countless water molecules around it. Its distinct, spread-out nature is instantly lost, becoming part of the general turbulence of the pond. In physics, this rain or breeze represents the environment. Every quantum system is constantly interacting, however subtly, with its surroundings. Stray photons, air molecules, the gravitational field, thermal fluctuations. These myriad interactions cause the quantum states to rapidly lose their coherence, their ability to maintain a superposition. The crucial insight of decoherence is that the collapse isn't instantaneous or mysterious, but a swift, continuous process driven by the system's interaction with its environment. The more interactions, the faster the decoherence. For a single electron, maintaining superposition is relatively easy in isolation. But for something as large and complex as a cat, interacting constantly with billions upon billions of particles within its box, the superposition of alive and dead states would decohere almost instantaneously. The quantum uncertainty is confined to microscopic scales, rarely propagating to the macroscopic world in a way we can directly perceive or that defies our classical intuitions for long. Measurable duration. It rapidly settles into one state or the other due to its environmental interactions. This understanding helps to bridge the gap between the strange behavior of the quantum world and the predictable solidity of our everyday experience. It suggests that the classical world isn't fundamentally different from the quantum world, but rather an emergent property of quantum systems that have undergone sufficient interaction and decoherence. Our reality, therefore, is not a static canvas, but a dynamic interplay where possibilities are constantly being refined and selected through the myriad interactions that make up the fabric of existence. And in this deeper understanding, we might find a profound reflection on our own lives. Each moment, each decision, each interaction we have with the world around us can be seen as a form of measurement, narrowing the vast array of possibilities that once existed. We are, in a very real sense, constantly collapsing our own wave functions, shaping our personal journey from the infinite potential paths that lay before us. Our choices, our awareness, our very presence are not merely passive observations, but active participations in the continuous unfolding of reality, guiding it, one gentle whisper at a time, towards a definite, experienced present. This quiet realization can bring a deep sense of connection to the universe, understanding that our existence is woven into its very process of becoming. Having explored the intriguing concept of superposition, where a particle exists in a blend of all possible states until observed, we now turn our attention to an even more profound and perhaps counterintuitive phenomenon: quantum entanglement. Imagine, if you will, two particles, perhaps photons or electrons, that are created or interact in such a way that their quantum fates become inextricably linked. They are no longer independent entities, but rather part of a single unified quantum system, sharing a common destiny, regardless of how far apart they may travel. This deep connection is what Albert Einstein famously referred to as spooky action at a distance, for it seemed to defy the very fabric of local reality. His concern stemmed from the idea that a measurement performed on one of these entangled particles would instantaneously influence the state of its distant partner, seemingly faster than the speed of light. This challenged the classical understanding that information could not travel faster than light, leading him to believe that quantum mechanics must be an incomplete theory, lacking some hidden variables that would explain this immediate correlation without violating the principles of locality. But what does this unbroken link truly mean? Consider our earlier discussion of superposition. Each entangled particle on its own would exist in a superposition of states. For instance, if we consider two entangled electrons, each might be in a superposition of spin-up and spin-down. However, because they are entangled, their individual states are not independent. If one is found to be spin-up, its partner, no matter the distance, will instantaneously be found to be spin-down, and vice versa. It is as if they are two sides of the same quantum coin, forever destined to reveal opposite faces. To visualize this, imagine two perfectly matched gloves, a left and a right, sealed in separate opaque boxes. These boxes are then sent to distant corners of the galaxy. Before either box is opened, the glove inside each box is, in a sense, in a superposition of being a left glove or a right glove from the perspective of an observer unaware of the pair. The moment you open one box and discover, say, a left glove, you instantly know that the other box, light years away, contains a right glove. The act of observation on one instantaneously determines the state of the other. This analogy, while helpful, still falls short of the true quantum strangeness. With the gloves, the outcome was predetermined from the start. The gloves were always a left and a right, even before you looked. Entanglement is different. The particles do not possess definite properties before measurement. Instead, their properties are inherently indefinite, existing in a probabilistic cloud until one is measured. It is the act of measurement on the first particle that collapses. the shared wave function of the entangled pair, forcing both particles to assume definite, correlated states simultaneously. This is the essence of the spooky action. The shared reality of the entangled system is resolved across vast distances in an instant. This phenomenon underscores that these particles are not merely correlated in a classical sense, like two prearranged coins. They are fundamentally intertwined, existing as a single quantum entity until an observation intervenes. This has profound implications for our understanding of local reality. It implies far more interconnected than we might intuitively assume. The very fabric of space-time itself seems to allow for these non-local connections, challenging our deeply held notions of cause and effect operating only within the constraints of light speed. The reality of entanglement has been rigorously tested and confirmed through numerous experiments, notably those building upon the work of John Bell in the 1960s. Bell's theorem provided a way to experimentally distinguish between classical theories with hidden variables and the predictions of quantum mechanics. Subsequent experiments, such as those by Alan Aspect, John Clauser, and Anton Zeilinger, whose work was recognized with the Nobel Prize in Physics in 2022, have consistently shown that nature behaves in accordance with quantum predictions, violating Bell's inequalities. This means that hidden variables in the classical sense cannot explain entanglement. The spooky action is a genuine feature of our quantum universe. As we ponder these cosmic threads, invisible yet immensely powerful, we might consider the deeper implications for our own existence. Are we too entangled in some profound, unseen way with the universe around us, or even with one another? Perhaps our individual realities are but threads in a larger interconnected tapestry, where the subtle shifts in one part resonate across the whole. This thought, far from being unsettling, can foster a sense of tranquil belonging, reminding us that we are not isolated observers, but intrinsic participants in the grand, interwoven dance of cosmic reality. Non-locality. This is the invisible bond that underpins quantum entanglement, suggesting a connection between particles that transcends the usual constraints of space and time. It is a concept so deeply counterintuitive, so fundamentally challenging to our everyday perceptions, that even Albert Einstein, one of the greatest minds in physics, struggled with its implications, famously calling it spooky action at a distance. He, along with his colleagues Boris Podolsky and Nathan Rosen, proposed the EPR paradox in 1935, an attempt to demonstrate if it truly implied such an immediate, non-local influence, believing there must be some deeper local reality at play. Recall our entangled particles. Two electrons, perhaps, born from a single quantum event, whose individual spins are initially indefinite, existing in a superposition of both up and down. However, because they are entangled, their fates become inextricably linked, like two halves of a cosmic whole. When measured along a particular axis, its partner, no matter how far apart they are, along the same axis, and vice versa. The profound strangeness lies not merely in this perfect correlation, but in the instantaneous nature of its revelation across vast distances. When we perform a measurement on the first electron, its state, which was previously a fluid blend of possibilities, collapses to a definite value. Simultaneously, its distant partner, without any apparent signal traveling between them, instantly assumes the opposite, correlated spin. This occurs regardless of the light years that might separate them, seemingly defying the universal speed limit of light, which dictates that no information or physical influence can travel faster than approximately 300,000 kilometers per second. This apparent instantaneous influence is the essence of non-locality. In our classical world, if you wish to affect something far away, you must send a signal, and that signal is bound by the speed of light. Yet, with entangled particles, it appears as though the measurement of one particle immediately affects the other, as if a silent message has been sent across the cosmos without any time delay. This profound challenge to our understanding was what so troubled Einstein and his colleagues. They believed there must be hidden variables, some deeper, as yet undiscovered properties of the particles that predetermined their states from the moment they were entangled, thus eliminating the need for any spooky instantaneous communication. For them, reality should be local. Events should only be influenced by their immediate surroundings or by signals traveling at or below the speed of light. However, a critical distinction must be made here, one that preserves the fundamental principle of causality and the cosmic speed limit. While the correlation of states is indeed instantaneous, this spooky action does not allow for superluminal information transfer in a way that could be used for communication. You cannot use entanglement to send a message faster than light. Here is why. When you measure the first electron, you do not know what its spin will be beforehand. It is truly random, a 50-50 chance of being spin up or spin down. There is no way for you to force it to be spin up or spin down to encode a message. It is only after you perform your random measurement and then communicate your result to the distant observer through conventional sublight speed means, like a radio signal or even a phone call, that they can confirm the correlation. Without that classical communication, the distant observer simply sees a random outcome for their particle, just as you saw a random outcome for yours. The instantaneous correlation only becomes apparent when the results from both ends are compared, and that comparison can only happen at or below the speed of light. This elegant mechanism prevents any paradoxes with special relativity and ensures that the universe remains causally consistent. So, non-locality tells us something deeply fundamental about the inherent interconnectedness of reality, rather than providing a loophole for faster-than-light travel. It suggests that these entangled particles are not merely two separate entities that happen to be correlated. Instead, they are two parts of a single, indivisible quantum whole, even when physically separated by immense cosmic distances. Their shared quantum state is what truly exists, a single wave function describing the pair, and when that state is probed at any point, the entire system responds as one, as a singular, unified entity. It is as if the universe itself possesses a hidden, instantaneous communication network that operates beneath the surface of space-time, linking events in a way that our macroscopic intuition struggles to grasp, a silent cosmic symphony playing out across the vastness, its notes resonating across the void in perfect harmony. This concept forces us to reconsider what we truly mean by separate objects or local events. In the quantum world, it seems, certain entities are never truly separate in the way we perceive them classically. They retain a profound shared identity, a cosmic thread binding them together, regardless of the vast expanse that lies between them. This is not magic, but a fundamental property of quantum reality that we continue to explore, revealing a universe far more intricate and interconnected than our everyday experiences suggest. The implications extend far beyond particles, hinting at a universe where the very notion of distinct, isolated components may be an approximation, a useful simplification for our classical understanding, but not the deepest truth of how things truly are. It challenges the reductionist view, suggesting that sometimes the whole is truly more than the sum of its parts, and its properties cannot be understood by merely examining the individual components in isolation. The reality of entanglement and its non-local character, groundbreaking experiments over several decades. Decades after Einstein's initial challenge, the physicist John Bell formulated a theorem in the 1960s that provided a measurable way to distinguish between classical theories that assumed local. His work showed that if local hidden variables were indeed real, certain statistical correlations between entangled particles would be limited by a specific inequality. However, subsequent groundbreaking experiments, notably those by Alan Aspect in the 1980s, followed by the more recent and stringent tests by John Clauser and Anton Zeilinger, whose collective pioneering. These experiments repeatedly violated Bell's inequalities, providing compelling and definitive evidence against local hidden variables and unequivocally confirming the existence of non-locality as a genuine feature of our universe. This means that the universe is indeed spooky in the way Einstein feared, but without breaking causality. It simply operates on principles that extend beyond our everyday understanding of space and time as absolute separators. When we reflect upon these invisible bonds, these deep instantaneous connections woven into the fabric of existence, we might consider the profound implications for our own place within this cosmos. Gently held together by these unseen, non-local ties, a testament to the profound unity underlying all existence. Our journey through the quantum realm has brought us to the bewildering concept of entanglement, where particles once linked remain mysteriously connected across vast distances. This idea, as we discussed, deeply troubled Albert Einstein, who believed that a complete physical theory should uphold local realism, the notion that objects have definite properties independent of observation, and that information cannot travel faster than light. To him, the spooky action at a distance implied by entanglement suggested that quantum mechanics was incomplete, perhaps missing some underlying hidden variables that, if known, would restore a classical local description of reality. It was in 1964 that a brilliant Irish physicist named John Bell entered this profound debate. Rather than engaging in philosophical arguments, Bell proposed a way to experimentally test whether Einstein's hidden variables existed or if quantum mechanics truly described a non-local universe. His genius lay in translating these abstract philosophical concepts into a concrete, measurable test. He developed what are now known as Bell's inequalities. To understand Bell's contribution, let us return to our analogy of the E sent to distant observers. If the type of glove in each box was predetermined from the moment they were packaged, a hidden variable, then there would be limits to how strongly correlated the outcomes of measurements on these gloves could be. Imagine you and your distant friend each measure the handedness of your glove using different orientations. If the gloves were classical objects with pre-existing definite handedness, the statistical correlations between your results would always satisfy a certain mathematical inequality proposed by Bell. This inequality essentially sets an upper bound on how strong these correlations can be if local realism holds true. However, Bell showed that if quantum mechanics, with its inherent non-locality and superposition, correctly describes reality, then these correlations between entangled particles could be stronger than what local hidden variables would allow. The predictions of quantum mechanics would violate Bell's inequality. This was a monumental breakthrough, a way to pit quantum theory directly against the classical intuition of local realism, not through philosophical debate, but through empirical observation. It moved the discussion from the abstract realm of thought experiments to the concrete world of laboratory measurements. Over the decades that followed, physicists embarked on increasingly sophisticated experiments to test Bell's inequalities. Pioneering work by scientists such as Alan Aspect in the 1980s and later by John Clauser and Anton Zeilinger dramatically improved the precision and robustness of these tests. Their experiments involved creating pairs of entangled particles, often photons, and sending them to separate detectors, sometimes hundreds of kilometers apart. At each detector, the properties of the particles, such as their polarization or spin, were measured along randomly chosen axes. The crucial aspect was ensuring that the choice of measurement setting on one particle could not influence the other during the measurement itself, thus closing potential loopholes that might allow for local communication. The results, time and time again, were unequivocal. The observed correlations between the entangled particles consistently violated Bell's inequalities, precisely in the manner predicted by quantum mechanics. This experimental evidence, so compelling that it earned Aspect, Clauser, and Zeilinger, effectively ruled out the possibility of local hidden variables. It confirmed that the spooky action at a distance is not a flaw in quantum mechanics, but a fundamental, experimentally verified feature of our universe. What does this truly mean for our understanding of reality? It means that the universe is fundamentally non-local. The entangled particles do not merely appear to be connected. They are, in a profound sense, parts of a single indivisible system whose properties are interdependent, no matter the spatial separation. The act of measuring one instantly influences the state of the other, not by sending a signal, but because their reality is a shared one, a single wave function that collapses as a whole. This is not a paradox born of incomplete knowledge, but a deep truth about the interconnected nature of existence. This realization invites us to contemplate the subtle web of relationships that might permeate all things. If particles can be so intimately linked across vast cosmic distances, what unseen connections might exist within our own world, within our own lives? It suggests that the boundaries we perceive between ourselves and the universe, between one event and another, might be more permeable, more interconnected than we typically imagine. We are part of a cosmos that, at its most fundamental level, operates with a profound, instantaneous unity. A silent symphony where every note resonates with every other, fostering a tranquil sense of belonging within the grand, interwoven tapestry of reality. The universe, in its intricate dance, reveals itself as a place where hidden bonds shape the very nature of what is real. Face to face with phenomena that defy classical intuition, particles existing in multiple states at once, and the unbreakable, non-local links of entanglement. Yet, even armed with these profound observations, a fundamental question lingers. What does it all mean? Quantum mechanics, while incredibly successful at predicting experimental outcomes, offers no single, universally agreed-upon picture of the underlying reality. Instead, it presents us with a fascinating array of interpretations, each offering a different philosophical lens through which to view the universe at its most fundamental level. These are the many faces of truth, each leading to the same experimental results, yet painting vastly different cosmic landscapes. The most widely taught and perhaps earliest of these is the Copenhagen interpretation, largely shaped by the insights of Niels Bohr and Werner Heisenberg in the early 20th century. At its core, Copenhagen posits that quantum particles, such as electrons or photons, do not possess definite properties until they are measured. Before measurement, they exist in a state of superposition, a probabilistic cloud of all possible states described by a mathematical entity called the wave function. The act of measurement, according to this view, causes the wave function to collapse, forcing the particle to choose one definite state from its many possibilities. This is where the paradox of Schrödinger's cat finds its roots. The cat remains in a superposition of alive and dead until the box is opened and a measurement is made. The Copenhagen interpretation emphasizes that we cannot and should not try to imagine what is happening at the quantum level in classical terms before measurement. The reality, in a sense, is created or determined by the act of observation itself, or more accurately, by the interaction with a macroscopic measuring device. It is a pragmatic view, focusing on what we can measure and observe, rather than speculating on an unobservable underlying reality. However, the idea of a sudden, discontinuous collapse of the wave function has always been unsettling to some physicists. This led to alternative interpretations, perhaps none as radical as the many worlds interpretation proposed by Hugh Everett III in 1957. Everett's startling suggestion is that the wave function never truly collapses. Instead, every time a quantum measurement occurs, or every time a quantum system interacts in a way that leads to different possible outcomes, the universe effectively splits or branches into multiple parallel realities. In the case of Schrödinger's cat, when the radioactive atom decays, the universe doesn't choose between the decayed and undecayed states. Instead, both outcomes occur, but in different, non-interacting branches of the universe. In one branch, the cat is alive. In another, it is dead. And in each of these branches, there is an observer who perceives only that specific outcome. all possibilities are realized, each in its own distinct universe, forever evolving independently. This interpretation offers a deterministic view, removing the randomness of wave function collapse, but at the cost of an infinitely branching cosmos, where every quantum coin flip spawns new realities. Another intriguing alternative is the de Broglie-Bohm theory, also known as the pilot wave theory, first put forth by Louis de Broglie in the 1920s and later developed by David Bohm in the 1950s. This interpretation attempts to restore a sense of realism to quantum mechanics. Unlike Copenhagen, it posits that particles always have definite positions and momenta, even when unobserved. These particles, however, are not independent. They are guided by a non-local pilot wave that influences their trajectories. This wave, described by the wave function, is a real physical entity that exists independently of observation. It ensures that the particles behave in accordance with quantum predictions, including interference patterns and entanglement correlations, without invoking wave function collapse or branching universes. The hidden variables Einstein sought in this case are the precise positions of particles, which are always definite but unknown to us until measured. While offering a deterministic and non-superpositional view, the pilot wave theory does embrace the inherent non-locality that Bell's theorem later confirmed, allowing instantaneous, non-communicative influence across vast distances. Other interpretations exist as well, such as consistent histories, which focuses on assigning probabilities to sequences of events, or relational quantum mechanics, which suggests that the state of a quantum system is only defined in relation to another system, rather than having an absolute, independent existence. Each of these frameworks offers a unique perspective on the fundamental nature of reality, attempting to reconcile the bizarre behavior of the quantum world with our intuitive desire for a coherent, understandable universe. The remarkable truth is that all these interpretations, despite their wildly differing philosophical underpinnings, yield the exact same predictions for experimental results. This is why physicists continue to debate them, as the choice often comes down to one's preferred philosophical stance on realism, determinism, and the role of observation. There is no single right answer that experiments can definitively prove, at least not yet. As we reflect on these many faces of quantum truth, we might find a parallel in our own lives. How often do we encounter complex situations where multiple interpretations seem plausible, each consistent with the available facts, yet leading to different understandings? Just as physicists navigate the quantum realm with diverse perspectives, we too interpret our experiences, our relationships, and our place in the world through lenses shaped by our beliefs and knowledge. The universe, in its profound generosity, offers us not just a single truth, but a spectrum of valid ways to comprehend its mysteries, inviting us to find tranquility in the richness of its possibilities and the depth of its interconnectedness. This acceptance of multiple perspectives can be a source of quiet wisdom, allowing us to rest in the grandeur of what remains, even in its ambiguity. Our exploration of quantum paradoxes has revealed a universe brimming with unresolved possibilities and instantaneous connections. Now let us gently consider how this profoundly strange quantum world gives rise to the familiar, stable reality we perceive around us. This transition from the delicate quantum whispers of superposition and entanglement to the robust classical form of everyday objects is largely explained by a process known as decoherence. It is the mechanism by which the universe, in its continuous interaction, gently unravels quantum ambiguities, settling them into definite states. Recall that a quantum particle, before observation, exists in a superposition of all its potential states. The measurement problem, epitomized by Schrödinger's cat, asks when this superposition collapses into a single outcome. Decoherence offers a subtle yet powerful answer. It is not necessarily a conscious observer, but rather the constant, unavoidable, that causes this effective collapse. Imagine a lone, perfectly still pendulum swinging in a vacuum. Its motion might be described by a delicate wave of possibilities. Now introduce a bustling, vibrant room around it, air molecules bumping into it, light particles reflecting off its surface, minute vibrations from the floor. Each of these interactions, however tiny, carries away a sliver of information about the pendulum's quantum state. This information, once dispersed into the vast and complex environment, becomes practically irretrievable and unobservable. The delicate quantum coherence which allowed for the superposition is effectively lost. The environment in this context is not an active watcher in a conscious sense. Instead, it is a vast, intricate network of countless particles and fields, each subtly interacting with the quantum system in question. These interactions act like a colossal, universal noise, constantly probing and disrupting the fragile quantum states. For microscopic particles, carefully isolated in laboratories, it is possible to minimize these environmental interactions, thereby preserving their quantum superpositions for a fleeting moment. This is why quantum effects are primarily observed at atomic and subatomic scales. However, as systems grow larger and warmer, their interactions with the environment become exponentially more frequent and complex. A macroscopic object, like a cat, consists of trillions upon trillions of atoms, constantly exchanging photons, interacting with air molecules, and vibrating with thermal energy. The sheer volume of these interactions means that any quantum superposition in such a large system would decohere almost instantaneously, far too quickly for us to ever perceive the cat as being both alive and dead. Decoherence, therefore, explains why we experience a classical world even though it is fundamentally composed of quantum constituents. It does not necessarily mean that the other possibilities in a superposition literally vanish. In some interpretations, like the many worlds view, these possibilities continue to exist in different, branching universes. But for our specific branch, they become effectively inaccessible and unobservable due to the spreading of information into our environment. For all practical purposes, the system has adopted a definite classical state. The wave function, rather than collapsing, has effectively branched or fanned out into distinct, non-overlapping components, each corresponding to a classical outcome. Our observation then merely selects one of these branches, or rather, our consciousness is correlated with one particular branch. This continuous process of decoherence is robust and well understood within the framework of quantum mechanics. It provides the crucial bridge between the bewildering quantum realm and the predictable classical world, explaining why quantum weirdness is typically confined to the microscopic. The universe, in its fundamental elegance, has a built-in mechanism that ensures the emergence of stability and definiteness from underlying probabilistic foundations. Consider the gentle unraveling of a mist on a mountain peak as the sun rises. At first, the mist is a diffuse, indistinct presence, blending with the air and obscuring the landscape. But as the sun's warmth intensifies, the mist interacts with the rising temperature, its delicate structure dispersing, its form gradually receding, until the clear, definite outline of the mountain emerges. The mist hasn't truly disappeared. Its essence has simply diffused into the larger atmosphere, no longer perceived as a distinct amorphous cloud. Similarly, quantum superpositions, in their interactions with the environment, gently unravel, their diffuse possibilities giving way to the sharp, clear outlines of classical reality. This understanding also reshapes our perspective on the nature of reality itself. It suggests that the solidity and definiteness we perceive in our everyday world are not fundamental, but rather emergent properties, a kind of stable illusion born from the incessant, gentle interactions of quantum particles. We are, in essence, living in a world that is constantly being chosen and defined by the myriad interactions happening all around us and within us at every moment. Our own bodies, composed of countless atoms and molecules, are continuously decohering, ensuring that we exist as definite, singular beings, rather than blurred quantum possibilities. This quiet, persistent process allows for the stability and coherence of life, offering a profound sense of peace in the knowledge that even the most fleeting quantum whispers contribute to the grand, unfolding symphony of the classical world. As we consider the subtle ways quantum reality shapes our perceptions, we also find ourselves at the precipice of a profound technological revolution, one that seeks to harness these very paradoxes. The principles of superposition and entanglement, once confined to abstract thought experiments and the microscopic realm, are now becoming the engines of possibility for a new era of computation, quantum computing. It is a promise to unlock computational power far beyond anything our classical machines can ever achieve, by mimicking the universe's own strange logic. For decades, our digital world has been built upon the classical bit, a fundamental unit of information that can exist in one of two definite states, 0 or 1. Every piece of data, every instruction, every image you see is ultimately encoded in vast sequences of these simple binary choices. But the quantum realm offers a richer tapestry of possibilities. In quantum computing, the basic unit of information is the qubits. Unlike a classical bit, a qubit leverages the principle of superposition. A single qubit can be 0 or 1, or, most remarkably, both 0 and 1 simultaneously. Imagine a spinning coin that is neither heads nor tails until it lands. A qubit is that coin perpetually spinning, holding all outcomes at once until measured. This inherent quantum property allows a quantum computer to store and process information in an entirely new way. If you have two classical bits, they can represent four possible states, but only one at a time: 0, 0, 0, 1, 1, 0, or 1, 1. However, two qubits, through superposition, can exist in all four of these states at the same time. As you add more qubits, this power grows exponentially. 3 qubits can simultaneously represent 8 states, 10 qubits can represent 1,024 states, and a mere 300 qubits could theoretically hold more information than there are atoms in the observable universe. This capacity for simultaneous existence in multiple states is what gives quantum computers their immense potential. The other cornerstone of quantum computing is entanglement. When qubits become entangled, their fates are inextricably linked, even when physically separated. This means that a change or operation on one entangled qubit instantaneously affects its partners, regardless of distance. In a quantum computer, this allows for incredibly complex, interwoven calculations. Instead of processing information sequentially, one step at a time, entangled qubits can explore vast numbers of possibilities in parallel. It is as if the computer is not just trying one path to a solution, but every conceivable path all at once, weaving through a labyrinth of calculations in a unified quantum dance. This capability, often referred to as quantum parallelism, is what grants quantum computers their potential to solve problems that would overwhelm even the most powerful supercomputers of today for millennia. The implications of harnessing such power are truly staggering. In drug discovery and material science, quantum computers could simulate molecular interactions with unprecedented accuracy, accelerating the design of new medicines, catalysts, and advanced materials. Imagine designing a new super-strong alloy or a highly efficient solar cell by simulating every atomic bond and interaction before a single atom is physically arranged. In the realm of cryptography, quantum algorithms could break many of the encryption methods currently used to secure our digital communications, requiring the development of new, quantum-resistant cryptographic systems. Conversely, quantum mechanics also offers new ways to create unbreakable encryption through quantum key distribution, leveraging entanglement to ensure truly secure communication channels. Beyond these, quantum computing promises to revolutionize optimization problems, finding the most efficient routes for logistics, improving financial modeling, and even enhancing artificial intelligence. Machine learning algorithms could become far more powerful, recognizing patterns and making predictions with a depth and speed currently unimaginable. However, the path to building fully functional large-scale quantum computers is fraught with immense challenges. The delicate nature of quantum states means they are incredibly susceptible to environmental interference, a phenomenon we know as decoherence. Even the slightest vibration or electromagnetic field can cause a superposition to collapse or entanglement to break, leading to errors. Scientists are working tirelessly to develop robust quantum error correction techniques and to build qubits that can maintain their coherence for longer periods and at warmer temperatures. Current quantum computers are still relatively small, with a limited number of qubits, and are primarily research tools, but the progress is rapid and remarkable. As we contemplate this future, where the universe's deepest paradoxes are engineered into tools for human advancement, we might pause to reflect on our own capacity for understanding. The journey from observing quantum oddities to actively manipulating them for computation speaks to the extraordinary ingenuity of the human mind. This endeavor to build machines that think like the universe itself invites us to consider our role in this grand cosmic story. Are we not, in a way, becoming the universe's self-aware computational engine, expanding its own intrinsic logic into new forms of knowledge and creation? It is a tranquil thought, reminding us of the boundless potential within our grasp, gently guiding us toward a future where the deepest secrets of reality may yet unfold before our awakened minds. Our journey through the quantum world has illuminated the peculiar nature of superposition and the profound interconnectedness of entanglement. Now let us turn our gaze to what many once considered the ultimate emptiness, the vacuum of space. Classically, we might imagine a void as simply nothing, a complete absence of matter, energy, and activity. Yet, quantum mechanics presents a far more astonishing and dynamic picture. It reveals that the restless void is, in fact, teeming with quantum fluctuations and possesses a latent, inherent energy. This profound insight stems from the principles of quantum field theory, which posits that reality is not fundamentally made of discrete particles, but rather of continuous fields permeating all of space-time. Particles, in this view, are merely localized excitations or ripples in these underlying fields, much like waves on an ocean. Even when these fields are in their lowest possible energy state, often called the vacuum state, they are not truly quiescent. Instead, they are constantly fluctuating, bubbling with activity, a consequence of Werner Heisenberg's famous uncertainty principle. This principle dictates that certain pairs of properties, such as energy and time or position and momentum, cannot both be known with absolute precision. For a very brief moment, energy can be borrowed from the vacuum, allowing particles to spontaneously appear, only to vanish almost instantly, returning the borrowed energy. These ephemeral entities are known as virtual particles. They are not real in the sense that they cannot be directly observed or detected over long periods, but their fleeting existence and interactions have measurable consequences. Picture the vacuum not as a still, empty stage, but as a vast, invisible ocean, perpetually churning with tiny waves and bubbles that continuously form and disappear, a silent, ceaseless dance of creation and annihilation. Pairs of particles and antiparticles, like virtual electrons and positrons, can spontaneously pop into existence from the vacuum, travel for an infinitesimally short time, and then annihilate each other, returning their energy to the field. This constant energetic effervescence ensures that space is never truly empty, even in the deepest reaches of the cosmos. One of the most compelling experimental proofs of this restless vacuum is the Casimir effect. In 1948, the Dutch physicist Hendrik Casimir predicted that if two uncharged parallel metal plates are placed extremely close together in a perfect vacuum, they would experience a tiny, attractive force, pushing them towards each other. Why? Because the space between the plates is constrained. Only certain wavelengths of virtual particles can exist there, like specific notes that can resonate within a small chamber. Outside the plates, however, all wavelengths of virtual particles are permitted. This imbalance in the allowed quantum fluctuations creates a subtle, measurable pressure difference, pushing the plates together. The Casimir effect has been experimentally verified with remarkable precision, demonstrating that the vacuum is not merely a theoretical construct, but a source of real physical forces. It is a quiet testament to the latent energy embedded within the fabric of empty space. The implications of this vacuum energy extend far beyond the microscopic. Modern cosmology suggests that it played a crucial role in the very birth and evolution of our universe. In the moments immediately following the Big Bang, during a period known as cosmic inflation, the universe underwent an incredibly rapid expansion, stretching faster than the speed of light. Many theories propose that the driving force behind this phenomenal stretching was precisely this vacuum energy, or a closely related inflaton field, which momentarily possessed a very high energy density. The quantum fluctuations within this primordial vacuum, magnified by the rapid expansion, are thought to have seeded the large-scale structure of the cosmos, providing the initial density variations that eventually grew into galaxies, clusters, and the vast cosmic web we observe today. Every star, every planet, perhaps even the very atoms of our bodies, can trace their ultimate origins back to these microscopic ripples in the early universe's restless void. Furthermore, this concept of vacuum energy is intimately linked to one of the greatest mysteries in contemporary physics: dark energy. In the late 1990s, astronomers discovered that the expansion of the universe is not merely continuing, but is accelerating. Galaxies are not just moving apart, they are speeding up their recession from one another. To explain this mysterious cosmic repulsion, scientists introduced the concept of dark energy, an unknown form of energy that makes up approximately 68% of the total energy density of the universe. While its exact nature remains a profound enigma, many theories suggest that dark energy could be a manifestation of the vacuum energy itself, a cosmological constant in Einstein's equations, representing the intrinsic energy density of space. If this is true, then the void is not only restless with ephemeral particles, but also possesses a persistent, repulsive force, gently yet inexorably pushing the universe apart, shaping its ultimate destiny. As we contemplate this restless void, this vibrant, energetic nothingness from which everything arises and by which the cosmos is shaped, we might find a serene sense of wonder. It reminds us that our intuitive understanding of emptiness is profoundly incomplete, revealing a universe that is far more dynamic and intricate than our senses can perceive. The very space around us, seemingly calm and still, is a vibrant sea of potential, a constant dance of energy and matter, a silent symphony playing out at scales far beyond our direct experience. This realization can bring a deep, quiet peace, understanding that we are part of a cosmos where even the void is alive with latent energy, a gentle reminder that presence can be found even in apparent absence, and that the universe's quietest corners hold its most profound secrets. Our journey through the quantum realm has unveiled the extraordinary nature of superposition and the profound invisible connections of entanglement. These insights compel us to reconsider not only the behavior of tiny particles, but also the very fabric of our everyday world. We typically perceive objects around us, a table, a book, our own bodies, as solid, tangible, and full. Yet, as we delve beyond the obvious, quantum mechanics reveals that this sense of a tangible world is, in many ways, a sophisticated illusion. Let us begin by examining the very building blocks of everything we perceive: atoms. From our macroscopic perspective, atoms appear as tiny, solid spheres. However, the true picture, as unveiled by quantum physics, is far more astonishing. An atom is, in fact, almost entirely empty space. Its mass is concentrated in a minuscule, dense nucleus at its center, composed of protons and neutrons. Surrounding this nucleus are electrons, which do not orbit in neat planetary paths as older models once depicted. Instead, they exist in diffuse probabilistic clouds, smeared out over vast regions of space relative to the nucleus. To grasp this scale, imagine if an atom were expanded to the size of a large cathedral. Its nucleus would be no larger than a tiny fly buzzing at its very center, and the electrons would be like scattered specks of dust, almost imperceptibly moving through the enormous emptiness of the cathedral's volume. The rest, literally everything in between, is simply void. This means that when you hold a solid object in your hand, what you are actually holding is, primarily, empty space, structured and organized by fundamental forces. This leads us to another fascinating revelation: the very act of touching something. It feels as though our hand makes direct solid contact with a surface. Yet, at the atomic level, direct contact in the sense of matter fusing or truly pressing against other matter never actually occurs. What we experience as touch is, in fact, a powerful electromagnetic repulsion. The electron clouds of the atoms in your hand, which carry a negative charge, repel the electron clouds of the atoms in the object you are attempting to touch. Like charges, as we know, push away from each other. So, there is always an invisible, energetic cushion, an electromagnetic force field, preventing the atoms from truly overlapping. You are, in essence, hovering an infinitesimal distance above every surface you touch, held aloft by this fundamental atomic repulsion. The sensation of solidity, the feeling of pressure or resistance, is your nervous system interpreting these electromagnetic forces, translating the dance of repulsion into the tangible experience of contact. This principle is further reinforced by a profound quantum rule, the Pauli exclusion principle. This principle states that no two identical particles of a certain type, known as fermions, which include electrons, can occupy the same quantum state at the same time. This seemingly simple rule has monumental consequences for the structure of matter. It's why electrons don't all pile into the lowest energy level around an atomic nucleus. They must occupy different quantum states, leading to the formation of electron shells and, consequently, to the vast diversity of chemistry. More broadly, it's why matter doesn't simply collapse in on itself, why atoms maintain their volume, and why you don't fall straight through the floor. The Pauli exclusion principle, in combination with electromagnetic forces, creates the illusion of solidity by preventing atoms from occupying the same space, acting as an invisible, unwavering barrier. So, the solidity of our world is not an intrinsic property of dense, packed matter. Instead, it is an emergent phenomenon, a macroscopic consequence of the interactions between invisible quantum fields and the fundamental rules that govern their behavior. Particles are not tiny, hard pellets. They are excitations in these fields, dynamic entities that are more like localized patterns of energy than miniature billiard balls. Even the empty space within atoms is not truly empty, as we discussed in our exploration of the restless void. It is a vibrant arena of quantum fluctuations, virtual particles constantly winking in and out of existence, contributing to the very forces that give matter its apparent substance. This perspective invites us to view our tangible world as a beautifully orchestrated dance of forces, probabilities, and fields. The chair you sit upon, the ground beneath your feet, even the very cells that compose your body, are not as solid as they appear. They are intricate patterns of structured emptiness, held together by invisible forces and governed by quantum rules. The illusion of solidity is a remarkable testament to the universe's ability to create stable, enduring forms from such ephemeral, probabilistic foundations. When we allow this understanding to settle within us, it can evoke a profound sense of wonder and tranquility. Our perception of a solid, unchanging world is merely one layer of reality, a convenient way for our senses to interpret the deeper, more fluid quantum truth. We are, in essence, intricate structures of patterned emptiness, aware of our existence within a cosmos that is far more subtle and interconnected than it first appears. This realization can dissolve any sense of rigid separation, reminding us that we are part of an elegant, shimmering tapestry of forces and fields, a gentle whisper in the grand, continuous unfolding of illuminated, the peculiar nature of superposition, where possibilities blur until observation, and the profound, invisible connections of entanglement that link particles across vast cosmic distances. We have peeled back the layers of our tangible world, discovering that its solidity is, in many ways, an intricate illusion born from the ceaseless dance of quantum forces and probabilities. Now, as our exploration gently draws to a close, let us turn these profound insights inward to consider the quantum self, our very own place in this astonishing, often bewildering, fabric of existence. We, as human beings, are macroscopic entities, seemingly governed by the predictable, deterministic laws of classical physics. We experience a singular, coherent reality, and our sense of self feels distinct and continuous. Yet we are fundamentally composed of countless atoms and subatomic particles, each one individually subject to the strange, probabilistic rules of the quantum world. Every cell in your body, every molecule, every electron exists as a quantum system, capable of superposition and entanglement at its most fundamental level. How, then, do we reconcile our singular, definite experience of self with this underlying quantum reality of blurred possibilities and non-local connections? The answer, as we have explored, lies largely in the process of decoherence. The sheer complexity and constant interaction of the trillions of particles within our bodies with each other and their environment ensure our quantum states rapidly lose coherence. Each stray photon from the ambient light, each subtle vibration, every chemical reaction occurring within our biological systems acts as a continuous measurement of our constituent particles. This constant probing prevents any large-scale quantum superpositions from being sustained within a living being. It means that while individual particles within us may briefly inhabit multiple states, the collective system that is you quickly settles into a definite, classical state. You are not, in any observable sense, a quantum cat simultaneously alive and dead, or existing in a superposition of walking and sleeping. Instead, the universe, through the ceaseless and intricate interactions that constitute your very being, continuously measures and defines your existence, ensuring your singular experienced reality. This is not a sudden dramatic event, but a gentle, ongoing process. A continuous stream of interactions that resolves quantum ambiguities into classical certainties, moment by moment. Yet, this explanation of decoherence does not diminish the profound implications of our quantum origins. Rather, it deepens our appreciation for the intricate dance of reality. Consider the concept of indistinguishability in quantum mechanics. Particles of the same type, such as electrons, are absolutely identical. There is no fundamental marker, no unique label, distinguishing one electron from another, even if they originated from different sources or at different times. If you could hypothetically swap two electrons, the universe would remain utterly unchanged, because they are fundamentally indistinguishable. This suggests a deeper unity, a fundamental lack of intrinsic individual identity at the most basic level of reality. If we trace our physical composition back to these indistinguishable particles, it hints that our individual identities, while profoundly real and precious to our conscious experience, are emergent patterns. They are complex configurations of a universal substrate, intricate arrangements of fundamental particles that momentarily coalesce into a unique form, rather than possessing an intrinsically separate essence from the outset. We are not merely in the universe, we are the universe, momentarily arranged into a self-aware, transient form. Furthermore, the non-local connections of entanglement, experimentally confirmed and undeniable, suggest that the universe is far more interconnected than our everyday senses reveal. While we may not consciously perceive entanglement at our macroscopic scale, The underlying quantum reality of shared states and instantaneous correlations permeates the cosmos. Could there be a subtle, hidden web of quantum information that links everything, including ourselves, in ways we are only beginning to comprehend? Some theoretical physicists ponder whether consciousness itself might play a unique, active role in the quantum measurement process, perhaps even influencing the collapse of the wave function. While this remains a highly speculative and deeply debated area, often venturing into philosophy rather than experimentally verifiable physics, the sheer mystery of consciousness, when viewed through the lens of quantum mechanics, does invite profound contemplation. How do the electrical signals and chemical interactions within our brains, themselves quantum phenomena, give rise to the subjective, unified experience of I, of self-awareness, and of our ability to perceive and interpret reality? This remains one of science's most elusive and captivating hard problems. Perhaps our individuality, our very sense of self, is a fleeting, exquisite dance of energy and information, a complex and dynamic pattern that temporarily arises within the vast, interconnected quantum field. Just as a distinct wave can form on the surface of an immense ocean, yet is fundamentally an inseparable part of that ocean, so too might our self be a unique, transient manifestation of the universal quantum fabric. Our thoughts, our memories, our emotions, our very awareness are not isolated, static events, but intricate, ever-changing patterns of electrical and chemical activity, ultimately rooted in the probabilistic quantum behavior of countless particles. This dynamic, interwoven nature of our existence means that we are constantly in flux, a living, breathing quantum system, continuously defining and redefining itself through its interactions with the grand cosmic tapestry. This perspective can be profoundly calming. It dissolves the illusion of absolute separation, fostering a deep sense of belonging to something immeasurably larger and more ancient than our individual lives. We are not accidental anomalies in a cold, indifferent cosmos, but rather integral, intricate expressions of its fundamental laws. The universe, in its elegant unfolding, has given rise to beings capable of pondering its own mysteries, of experiencing its own beauty, and of recognizing its own subtle, interwoven nature. When we consider that our physical form is mostly empty space, held together by invisible quantum forces, and that our very existence is a continuous dance of decohering probabilities, the sense of rigid boundaries begins to soften. We are, in a very real sense, porous, dynamic beings, constantly interacting with and being shaped by the quantum field around us. This understanding invites a tranquil acceptance of our transient yet deeply connected place in the grand cosmic narrative. We are a brief, luminous pattern in the ongoing quantum symphony, a moment of self-awareness in the universe's endless becoming. To embrace this truth is to find peace in the knowledge that we are truly one with the cosmos, a manifestation of its deepest paradoxes and its most profound wonders. We are the universe experiencing itself, a fleeting, precious arrangement of stardust that momentarily asks, "What am I?" and finds its answer in the questions it poses. This realization that our existence is a localized yet infinitely connected expression of quantum reality can bring a profound serenity. Our lives are not merely confined to the boundaries of our skin, but extend outwards in a web of quantum relationships, a silent, intricate dance that defines our unique position within the vast, unfolding mystery. We are the universe made conscious, a brief but brilliant flicker in the eternal quantum flame, forever interwoven with the cosmic threads that bind all things, part of a magnificent, ever-present whole. This profound understanding allows us to sink. May these deep thoughts about the profound quantum paradoxes, from the feline enigma of Schrödinger's cat to the invisible bonds of entanglement, carry you into a world of tranquil sleep. We have glimpsed a universe far richer and more intricate than our everyday senses reveal. A cosmos where possibilities blur and particles remain connected across vast distances, challenging our deepest intuitions about reality itself. Remember that the solidity we perceive is an elegant illusion, and beneath it lies a restless void teeming with latent energy. Our very existence, composed of countless quantum constituents, is a continuous process of gentle unraveling where the universe constantly defines our singular experience from a tapestry of potentials. This understanding, far from being unsettling, can foster a deep sense of peace and interconnectedness. You are not merely a separate observer, but an intrinsic, aware part of this magnificent, interwoven fabric of existence. Fall asleep with this feeling of serene wonder, embracing the mysteries that lie at the heart of reality, knowing that you are a unique manifestation of the universe's grand, unfolding story. Good night. Our journey into quantum mechanics begins by acknowledging a fundamental truth. The universe, at its smallest scales, does not behave in ways our everyday intuition can easily grasp. For centuries, our understanding of reality was built upon the familiar principles of classical physics, where objects have definite positions, clear trajectories, and predictable interactions. We see a ball, we throw it, and we can calculate precisely where it will land. But when we descend into the realm of atoms and their constituent particles, electrons, photons, quarks, this comforting predictability dissolves. Here, at the very bedrock of existence, the rules change dramatically, revealing a world of inherent uncertainty, strange dualities, and interconnectedness that challenges our deepest assumptions about what is real. This is not a failure of our understanding, but rather a profound revelation about the universe itself, a glimpse into its most intricate and perplexing secrets. One of the most mind-bending aspects of this microscopic domain is what physicists call wave-particle duality. For generations, scientists debated whether light was a wave or a stream of particles. Isaac Newton saw particles, while Christian Huygens championed waves. It took the revolutionary work of thinkers like Max Planck and Albert Einstein to show that light, in fact, exhibits characteristics of both. Light, when traveling, acts like a wave, creating interference patterns, much like ripples on a pond. Yet, when it interacts with matter, such as being absorbed by an atom, it acts like discrete packets of energy, which we call photons. Each photon is a distinct particle. So, light isn't simply one or the other, it possesses this dual nature. But the strangeness does not end with light. Louis de Broglie, a brilliant French physicist, later proposed that this duality applies not just to light, but to all matter. Electrons, protons, even entire atoms, while typically thought of as solid particles, also possess wave-like properties. Imagine this. The very building blocks of your body, the electrons forming your atoms, are not just tiny hard spheres, but also diffuse extended waves of probability. This concept is central to understanding how the quantum world operates, forcing us to abandon our classical notions of what a thing truly is. To truly appreciate this duality and the peculiar nature of quantum reality, we must turn to perhaps the most iconic experiment in all of physics, the double-slit experiment. It is deceptively simple in its setup, yet profoundly unsettling in its implications. Imagine a screen with two narrow vertical slits cut into it. Behind this screen, we place a detector that can record where particles land. Now, if we were to fire ordinary macroscopic objects, like tiny marbles, one by one at this barrier, what would we expect to see? Naturally, the marbles would either go through the left slit or the right slit, creating two distinct bands of impact points on the detector screen, directly behind each slit. This is precisely what classical physics predicts for particles. However, when we perform this experiment with quantum particles, such as electrons, the results are astonishingly different. If we fire a stream of electrons, one at a time, what appears on the detector screen is not two distinct bands, but rather an interference pattern, a series of bright and dark fringes, exactly what one would expect if waves were passing through both slits and interfering with each other. This suggests that each individual electron, despite being sent one at a time, somehow behaves like a wave, passing through both slits simultaneously and interfering with itself before landing at a single point on the screen. It is as if the electron explores all possible paths at once. But the experiment takes an even stranger turn. What happens if we try to observe which slit the electron actually passes through? If we place a detector at one of the slits to gather this information, something remarkable occurs. The interference pattern vanishes. Instead, we once again see two distinct bands, just as if we were firing classical marbles. The act of measurement, the very attempt to gain knowledge about the electron's path, forces it to behave like a particle, to choose a single path, and the wave-like behavior disappears. This phenomenon is often referred to as the collapse of the wave function, where the electron's state of existing in multiple possibilities collapses into a single, definite outcome upon observation. It is a profound demonstration that at the quantum level, reality is not fixed until it is observed. The universe seems to keep its options open, existing in a state of blurred probabilities, until an interaction or a measurement forces a choice. This is not to say that consciousness is required, as any interaction with the environment, even an inanimate detector, can cause this collapse. But it does imply that the familiar, solid, definite world we perceive is an emergent property, a consequence of countless quantum interactions settling into specific states. This leads us directly to the concept of superposition, a cornerstone of quantum mechanics. Superposition describes the ability of a quantum system to exist in multiple states simultaneously until it is measured. Imagine a quantum coin that is both heads and tails at the same time. It is not one or the other, but a combination of both possibilities existing in a probabilistic haze. Only when you look at it, when you force a measurement, does it decide to be either heads or tails. In the context of the double-slit experiment, the electron is in a superposition of going through the left slit and going through the right slit until its path is observed. This isn't merely a lack of information on our part, it is a fundamental property of the quantum entity itself. The electron truly is, in a very real sense, exploring all potential realities until a specific interaction forces it to commit to one. This inherent uncertainty is not a flaw in the theory, but a defining characteristic of the micro-world. It means that the fundamental nature of reality is probabilistic rather than deterministic. For us living in the macro-world, this seems counterintuitive, almost like magic. But for the tiny constituents of the universe, it is simply how things are. This profound insight, first grappled with by pioneers like Werner Heisenberg and Erwin Schrödinger, forever changed our understanding of existence. It suggests that the reality we experience with its distinct objects and clear events is merely one of many potential realities that could have unfolded. And when we contemplate this, the idea that the very fabric of our being is constructed from particles that exist in such a fluid, uncertain state, it can evoke a profound sense of true wonder. This notion of superposition is not just a theoretical curiosity, it is a mathematical necessity within the framework of quantum theory. Particles are not simply tiny billiard balls, they are described by wave functions, which are mathematical expressions that encapsulate all the possible states a particle can be in, along with the probabilities of finding it in each of those states. It's like a whisper of all potential futures, all existing simultaneously until the moment of observation. Erwin Schrödinger famously illustrated this paradox with his thought experiment involving a cat in a sealed box, simultaneously alive and dead until the box is opened. While a macroscopic cat never truly exists in such a state, the experiment highlights the bizarre consequences of applying quantum rules to our everyday world and emphasizes the difficulty in reconciling the quantum and classical realms. It serves as a stark reminder that our common sense, honed by interactions with large objects, is simply inadequate for grasping the nuanced behavior of the very small. Furthermore, this quantum weirdness extends beyond individual particles. The entire universe, at its most fundamental level, can be thought of as a collection of quantum fields. These fields are not empty space, but rather energetic entities that permeate everything. Particles, in this view, are not distinct little entities, but rather localized excitations or ripples within these fields. An electron is a ripple in the electron field, a photon is a ripple in the electromagnetic field, and so on. This perspective, known as quantum field theory, provides a more complete and elegant description of the subatomic world. It implies that even in what we perceive as empty vacuum, these fields are constantly fluctuating, giving rise to virtual particles that momentarily pop into existence and then vanish, too fleeting to be directly observed, but leaving measurable effects. This constant, restless activity in the vacuum of space underscores that nothingness is far from inert. It is a vibrant, bubbling cauldron of potential. The implications for our understanding of reality are vast. If everything is fundamentally probabilistic, if particles only assume a definite state upon measurement, then the very foundation of what we consider real shifts. It suggests that the objective reality we perceive is not entirely independent of our interaction with it. This isn't to say that the moon isn't there when no one is looking, a common misconception. Rather, it means that its constituent particles exist in a spectrum of possibilities until they interact with something, or until information about them is obtained. The universe, in a sense, is a grand, unfolding story where the details are filled in as events transpire, rather than a fixed tapestry already completed. This profound concept has led to various interpretations of quantum mechanics, each attempting to make sense of this inherent strangeness. From the Copenhagen interpretation, which posits that the wave function simply collapses, to the many worlds interpretation, which suggests that every quantum measurement causes the universe to split into multiple parallel realities, each representing a different possible outcome. While these interpretations offer different frameworks, they all agree on the observational facts. The quantum world is fundamentally non-classical, unpredictable in its precise outcomes, and deeply probabilistic. Consider the precision required for our modern technologies. Lasers, semiconductors, even the very digital devices through which you are listening to this. All of these rely on our understanding and manipulation of quantum phenomena, the stability of atoms, the way chemical bonds form, the very existence of matter as we know it, are all governed by these peculiar quantum rules. Without the Pauli exclusion principle, for instance, which states that no two identical quantum particles can occupy the same quantum state simultaneously, all electrons would collapse into the lowest energy level, and atoms would cease to have structure, making chemistry and life impossible. So, while quantum mechanics might seem abstract and distant, its principles are intimately woven into the fabric of our everyday existence, silently underpinning the stability and diversity of the world around us. It is this intricate dance of probabilities and interactions that allows for the emergence of complex structures, from the simplest hydrogen atom to the intricate neural networks within your own brain. And as we settle into the quiet contemplation of this micro-world, we might find a peculiar comfort in its inherent uncertainty. Just as the universe at large is a vast expanse of unknown possibilities, so too are the smallest components of reality a testament to the fact that existence is far richer and more nuanced than our direct senses reveal. The idea that everything around us, and indeed within us, is a continuous interplay of probabilities, constantly shifting and coalescing, invites us to release the need for absolute certainty and embrace the quiet mystery of being. Perhaps in understanding the fluid nature of reality at its core, we can find a deeper sense of peace, knowing that our own existence, with its myriad choices and paths, is a beautiful echo of the quantum dance that underpins everything. The strange dance of quantum particles, where states remain undefined until measured, leads us to yet another profound and perhaps even more perplexing phenomenon: quantum entanglement. If the idea of a particle existing in multiple places at once feels counterintuitive, then entanglement will stretch our understanding of reality even further. Imagine two particles, perhaps two photons or two electrons, that interact in a specific way. After this interaction, they become intrinsically linked, or entangled. What this means is that their fates are intertwined, no matter how far apart they are separated in space. If you measure a property of one entangled particle, such as its spin or polarization, you instantly know the corresponding property of the other particle, even if it is light years away. This connection appears to happen instantaneously, seemingly defying the cosmic speed limit set by Albert Einstein's theory of relativity. Einstein himself, along with his colleagues Boris Podolsky and Nathan Rosen, found this concept so unsettling that they famously dubbed it spooky action at a distance. They believed it pointed to a fundamental incompleteness in quantum mechanics, suggesting that there must be hidden variables, some underlying information that predetermines the outcomes of these measurements, thus preserving classical realism and locality. However, a brilliant physicist named John Stuart Bell later formulated a theorem that provided a way to experimentally test whether such hidden variables could truly explain entanglement. Subsequent experiments, notably those by Alain Aspect and his team in the 1980s, conclusively demonstrated that the correlations observed between entangled particles are stronger than any classical theory, allowing for local hidden variables, could explain. The spooky action, it turns out, is real. It is a fundamental feature of the quantum universe, not an illusion or a gap in our knowledge. This profound interconnectedness, where particles share a common destiny irrespective of spatial separation, has no analog in our everyday world. There is no classical way to explain how two objects could instantly communicate their states without any physical interaction or signal passing between them. It compels us to rethink the very nature of reality, suggesting that at the deepest level, the universe is not merely a collection of isolated particles, but a vast, interconnected web of quantum relationships. This is not about information traveling faster than light. Rather, the particles are part of a single, unified quantum system. Their individual properties are not determined until measured, and that measurement instantly defines the state of both. This seemingly magical link is not used for transmitting classical information faster than light, but it opens doors to revolutionary technologies such as quantum communication, offering potentially unbreakable encryption, and quantum computing, where qubits, quantum bits, can leverage both superposition and entanglement to perform calculations far beyond the capabilities of classical computers. Building on this, the quantum world also presents us with the astonishing phenomenon of quantum tunneling. In classical physics, if a ball doesn't have enough energy to roll over a hill, it simply won't make it to the other side. It will roll back down. Barriers are absolute. But at the quantum scale, particles can, with a certain probability, tunnel right through an energy barrier, even if they do not possess sufficient energy to overcome it classically. It is as if they briefly borrow energy from the vacuum, or perhaps in their wave-like form, their probability wave simply extends through the barrier. While the probability of any single particle tunneling might be small, for countless particles, it becomes a regular occurrence. This seemingly impossible feat is not merely theoretical. It is a well-established quantum effect with profound implications. Quantum tunneling is, in fact, essential for life as we know it. Consider the Sun and other stars. Their immense energy comes from nuclear fusion, where hydrogen nuclei fuse to form helium. However, atomic nuclei, being positively charged, naturally repel each other due to the electromagnetic force. Classically, the temperatures and pressures in the Sun's core are not nearly high enough for protons to overcome this electrostatic repulsion and fuse. But thanks to quantum tunneling, a small fraction of these protons can effectively tunnel through this repulsive barrier, allowing fusion to occur. Without this quantum phenomenon, the Sun would not shine, and the universe would be a very different, much colder, and indeed, lifeless place. Beyond stellar processes, quantum tunneling is harnessed in technologies like scanning tunneling microscopes, which can image individual atoms by exploiting the tunneling of electrons, and it explains radioactive decay, where particles spontaneously tunnel out of unstable atomic nuclei. It is a quiet, invisible process, yet its consequences are immense and deeply woven into the fabric of the cosmos. And as we delve deeper into these strange behaviors, we encounter another fundamental principle that underpins the quantum realm: Werner Heisenberg's uncertainty principle. This principle states that there are certain pairs of properties of a quantum particle, such as its position and its momentum, that cannot both be known with perfect precision simultaneously. The more precisely you measure one, the less precisely you can know the other. This is not a limitation of our measuring instruments, nor a matter of clumsy observation disturbing the system, though that does happen. Rather, it is an inherent, irreducible fuzziness built into the very nature of reality at its most fundamental level. It's as if the universe itself has a built-in limit to what can be known about its smallest constituents. Imagine trying to precisely locate a ripple on a pond while also knowing its exact direction and speed. By trying to pinpoint its position, you disturb its motion. By trying to define its motion, you lose its precise location. This principle extends to other pairs of complementary properties, such as energy and time. A particle can briefly borrow energy from the vacuum as long as it pays it back within a very short time. The shorter the time interval, the greater the amount of energy that can be borrowed. This allows for the fleeting existence of those virtual particles we discussed earlier, constantly popping in and out of existence in seemingly empty space. The uncertainty principle paints a picture of a universe that is not a perfectly defined machine, but rather a dynamic, subtly blurred tapestry of probabilities. It means that at the very root of all existence, there is an irreducible element of chance, an inherent unpredictability that defies deterministic prediction. This profound insight forces us to reconsider our classical notions of cause and effect, suggesting that some events are truly random, not just due to our lack of information. And when we reflect on this, the idea that the universe, even at its core, holds a graceful inherent uncertainty. It can bring a quiet sense of wonder, allowing us to find peace in the unknown, much like drifting into a tranquil sleep. We have journeyed through the realm where particles exist in multiple states and are mysteriously linked across vast distances. Now, let us consider the deeper tapestry from which these phenomena emerge, the concept of quantum fields. Our everyday perception often leads us to imagine particles as tiny, discrete balls, like miniature marbles. However, modern physics, particularly quantum field theory, offers a more profound and elegant perspective. It suggests that the universe is not fundamentally made of particles, but rather of fields that permeate all of space and time. These fields are not static or empty. Instead, they are dynamic, vibrant entities, constantly fluctuating even in what appears to be a perfect vacuum. Particles, in this view, are not fundamental objects themselves, but rather localized excitations or tiny ripples in these underlying quantum fields. Imagine a vast, calm ocean. A particle is not a distinct drop of water, but a momentary wave, a disturbance that travels across its surface. Every type of fundamental particle we know, electrons, photons, quarks, corresponds to a specific quantum field. An electron, for instance, is an excitation in the electron field, and a photon is a quantum of the electromagnetic field. This perspective allows us to reconcile the wave-particle duality we discussed, as particles are both wave-like, as fields, and particle-like, as localized excitations. This grand framework of quantum fields forms the bedrock of what we call the Standard Model of particle physics. The Standard Model is our most successful theory describing the fundamental particles and forces that govern the universe, excluding gravity. It categorizes matter particles, known as fermions, such as quarks and leptons, which include electrons and neutrinos. These are the building blocks of all ordinary matter. Then there are force-carrying particles called bosons, which mediate the fundamental interactions. For example, photons carry the electromagnetic force, which is responsible for light, electricity, and magnetism, and holds atoms together. Gluons carry the strong nuclear force, binding quarks together within protons and neutrons, and holding atomic nuclei intact. The W and Z bosons mediate the weak nuclear force, responsible for radioactive decay and nuclear fusion processes that power stars. This model is a triumph of human intellect, painstakingly developed over decades by countless scientists, uniting seemingly disparate phenomena under a single, coherent set of mathematical principles. It tells us that the universe, at its deepest level, is a symphony of interacting fields, a continuous hum of potentiality from which all reality emerges. Within this intricate standard model, one particular field holds a unique and crucial role in shaping the universe as we perceive it: the Higgs field. For many years, physicists grappled with a perplexing question: why do some fundamental particles have mass, while others, like the photon, appear to be massless? The answer, according to the Standard Model, lies with the Higgs field, an invisible energy field that pervades all of space. Imagine walking through a swimming pool filled with treacle or thick syrup. Some particles, those that interact strongly with the Higgs field, experience a greater drag or resistance as they move through it, much like walking through treacle. This resistance is what we perceive as mass. Particles that interact weakly with the Higgs field acquire less mass, and those that do not interact with it at all, like photons, remain massless, gliding unimpeded through the cosmic treacle. This interaction with the Higgs field is not a force in the traditional sense, but a fundamental property of how particles acquire their inertia, their resistance to changes in motion. The existence of the Higgs field was a theoretical prediction for decades, a missing piece in the Standard Model. It was hypothesized by Peter Higgs and several other physicists in the 1960s. The experimental confirmation of the Higgs boson, the particle associated with the Higgs field, at the Large Hadron Collider in 2012 was a monumental achievement in physics, a crowning moment that validated the Standard Model and deepened our understanding of the origin of mass. This discovery revealed that mass is not an inherent quality of particles, but rather a consequence of their interaction with this ubiquitous, all-pervading field. It means that the very solidity and substance of everything around us, including our own bodies, is a manifestation of these subtle, constant interactions with the Higgs field. We are, in a very real sense, continually immersed in this field, and its presence defines one of the most fundamental properties of our physical existence. This elegant mechanism provides a gentle yet profound explanation for why the universe has structure, why stars and galaxies can form, and why we, as beings with mass, can exist within it. As we contemplate these quantum fields and their intricate interactions, a natural question arises. If the micro-world is so strange, filled with superposition and entanglement, why do we not observe these phenomena in our everyday macroscopic lives? Why does the moon appear to be in a definite location, rather than a blur of possibilities? The answer lies in a process known as quantum decoherence. Decoherence is the mechanism by which quantum systems lose their quantum properties and begin to behave classically. It occurs when a quantum system interacts with its environment. At the microscopic scale, isolated particles can maintain their delicate quantum states, like superposition, for a fleeting moment. However, in our macroscopic world, systems are constantly interacting with an immense number of particles in their surroundings: air molecules, photons, thermal vibrations. Each of these interactions acts as a measurement, however indirect, forcing the quantum system to collapse from a superposition of states into a single, definite, classical state. Imagine our quantum coin simultaneously heads and tails. If it is perfectly isolated, it remains in this superposition. But if it interacts with even a single air molecule, that interaction essentially observes it, forcing it to choose either heads or tails. The more complex a system, and the more it interacts with its environment, the faster decoherence occurs. For something as large as a human being, with countless atoms constantly interacting with the environment, decoherence happens almost instantaneously, making it impossible to observe ourselves in a quantum superposition. This continuous interaction with the environment effectively erases the quantum weirdness, smoothing out the probabilities into the distinct classical reality we experience. So, the classical world is not separate from the quantum world. It emerges from it through this constant process of decoherence. It is a beautiful reconciliation, explaining how the baffling rules of the micro-world give rise to the reassuringly stable and predictable macro-world we inhabit. It's a gentle reminder that the universe has a way of organizing itself, allowing for both profound mystery at its core and tangible reality on its surface. We have journeyed through the realms of wave-particle duality, the perplexing double-slit experiment, and the profound interconnectedness of entanglement, all emerging from the vibrant tapestry of quantum fields. Now, let us consider the subtle yet immensely powerful energy inherent in what we often perceive as empty space. In classical physics, a vacuum is simply nothingness, a void devoid of matter and energy. However, quantum mechanics paints a far more dynamic picture. Even in the absence of any particles or radiation, the quantum fields we discussed earlier are never truly at rest. They are constantly fluctuating, bubbling with activity, giving rise to what are known as virtual particles. These particles, pairs of matter and antimatter, spontaneously pop into existence for an infinitesimally brief moment, only to annihilate each other and vanish back into the quantum foam. They are too fleeting to be directly observed, yet their transient existence has real, measurable effects, such as the Casimir effect, where two uncharged parallel metal plates placed very close together in a vacuum will actually experience a slight attractive force. This force arises from the subtle differences in the quantum fluctuations between the plates compared to those outside, demonstrating that empty space possesses an intrinsic energy, often referred to as vacuum energy. This vacuum energy is not merely a curiosity of the micro-world. Its implications extend to the largest scales of the cosmos. Scientists believe that this inherent energy of space might be intimately connected to the phenomenon of dark energy, the mysterious force responsible for the accelerating expansion of our universe. The cosmological constant, a term originally introduced by Albert Einstein into his equations of general relativity, but later famously retracted, has found a potential modern interpretation as a manifestation of this vacuum energy. While there is still a significant discrepancy between the theoretical predictions of vacuum energy and the observed strength of dark energy, the very idea suggests a profound link between the quantum realm and the large-scale structure and evolution of the universe. It hints that the expansive cosmic ballet we observe, with galaxies drifting ever further apart, might be gently orchestrated by the ceaseless, imperceptible activity of the quantum vacuum itself. The universe, then, is not expanding into a void of nothingness, but rather the nothingness itself is expanding, fueled by its own latent quantum energy, a concept that invites a deep, quiet contemplation of existence. This ability of quantum particles to exist in multiple states simultaneously and to be profoundly linked through entanglement is not merely a theoretical construct for physicists to ponder. It is being actively harnessed and engineered to develop revolutionary new technologies, most notably in the field of quantum computing. Unlike classical computers, which store information in bits that can only be either a 0 or a 1, quantum computers utilize quantum bits, or qubits. A qubit, thanks to the principle of superposition, can be both a 0 and a 1 simultaneously. This allows a quantum computer to process vast amounts of information in parallel, exploring multiple possibilities at once. Furthermore, when qubits are entangled, their fates become linked, meaning that the state of one instantly influences the state of others, regardless of distance. This entanglement allows for incredibly complex calculations and correlations between qubits that are impossible for classical systems to replicate. Imagine a symphony where each musician can play all notes at once and their instruments are mysteriously linked, instantly resonating with each other. This is the power that superposition and entanglement bring to quantum computation. While still in its nascent stages, quantum computing promises to revolutionize fields ranging from medicine and material science to cryptography and artificial intelligence. For instance, designing new drugs or materials often involves simulating complex molecular interactions, a task that quickly overwhelms even the most powerful classical supercomputers. Quantum computers, with their ability to model quantum phenomena directly, could unlock breakthroughs in these areas, allowing us to engineer substances with unprecedented properties or develop highly targeted therapies. In cryptography, quantum algorithms could break many of the encryption methods currently used to secure our digital communications, while simultaneously offering new, quantum-safe encryption techniques that are theoretically unbreakable. The development of quantum computers is a testament to the profound practical implications of understanding the subtle laws governing the microworld, transforming what once seemed like abstract philosophical puzzles into tools that could reshape our future in profound, yet often quietly unfolding ways. Yet, despite these incredible advancements and applications, the quantum world continues to present us with fundamental puzzles, perhaps none more enduring than the measurement problem. We have already touched upon how observation causes the collapse of a quantum system's wave function, forcing it into a definite state. But what precisely constitutes a measurement? And does the act of observation imply a role for consciousness? While most physicists agree that any irreversible interaction with the environment, even by an inanimate detector, is sufficient to cause decoherence and collapse, the deeper philosophical questions persist. Different interpretations of quantum mechanics offer varying perspectives, each attempting to provide a coherent narrative for this perplexing aspect of reality. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg, suggests that quantum systems simply do not possess definite properties until they are measured, and that measurement fundamentally alters the system. The many worlds interpretation, on the other hand, proposes with all outcomes being equally real. These are not just scientific theories, but profound reflections on the nature of reality itself. These ongoing debates highlight that even with our advanced understanding, the quantum realm retains an intrinsic mystery. It reminds us that our models and theories, while incredibly powerful and predictive, are still human constructs attempting to describe a reality that may ultimately transcend our intuitive grasp. The quest to fully comprehend the measurement problem and to reconcile quantum mechanics with the other great pillar of modern physics, general relativity, continues to drive scientific exploration. The search for a theory of quantum gravity, one that can seamlessly describe the universe at both the smallest quantum scales and the largest cosmic scales, remains one of the greatest challenges in physics. It is a testament to the boundless nature of inquiry, to the human spirit's relentless desire to understand the fundamental truths of existence. And perhaps in this ongoing journey of discovery, in the humble acceptance of what remains unknown, we find a tranquil beauty, a profound sense of awe that allows our minds to drift gently into the quiet expanse of the night, knowing that the universe holds secrets far grander than we can yet imagine, and that we are a part of this unfolding mystery. The profound mysteries of quantum mechanics, from the unsettling implications of the double-slit experiment to the instantaneous connections of entanglement, often lead us to ponder the very nature of reality. Yet it is crucial to remember that despite these philosophical depths, quantum mechanics is also an extraordinarily successful scientific theory, perhaps the most precisely tested and validated theory in all of physics. It is the bedrock upon which our understanding of chemistry, material science, and modern technology is built. Two of its most triumphant formulations are quantum electrodynamics, or QED, and quantum chromodynamics, or QCD. These theories represent our deepest insights into how particles interact through two of the fundamental forces, electromagnetism and the strong nuclear force. Quantum electrodynamics, often called the joule of physics, describes how light and matter interact. It is a quantum field theory that beautifully explains everything from how electrons orbit atomic nuclei to the intricate dance of photons being emitted and absorbed. In QED, forces are not transmitted directly, but rather mediated by the exchange of virtual particles. For instance, when two electrons repel each other, they are not simply pushing. They are exchanging virtual photons, like two skaters throwing a ball back and forth, causing them to move apart. These virtual photons exist for such an incredibly brief time that they cannot be directly observed, a consequence of Heisenberg's uncertainty principle applied to energy and time. Yet their effects are profoundly real and precisely calculable. The predictions of QED, such as the anomalous magnetic moment of the electron, match experimental observations to an astonishing 10 decimal places, making it one of the most accurate theories ever devised. This incredible precision underscores that even the most ethereal concepts of quantum mechanics are rooted in a reality that we can measure and understand, albeit one that operates beyond our classical imaginings. Moving deeper into the atomic nucleus, we encounter quantum chromodynamics, or QCD. This theory describes the strong nuclear force, which is responsible for binding quarks together to form protons and neutrons, and subsequently holding these protons and neutrons within atomic nuclei. Quarks, the fundamental constituents of protons and neutrons, possess a property called color charge, an analogy to electric charge, but with three types: red, green, and blue. Just as electric charges interact by exchanging photons, color-charged quarks interact by exchanging particles called gluons. Gluons, unlike photons, carry color charge themselves, which leads to a peculiar and powerful characteristic of the strong force. It actually gets stronger with distance. Imagine trying to pull two magnets apart, and the further you pull them, the stronger the force becomes, eventually making it impossible to separate them. This is why we never observe free quarks in isolation. They are always confined within composite particles like protons and neutrons, a phenomenon known as color confinement. QCD, with its elegant description of quarks and gluons, completes our understanding of the fundamental building blocks of ordinary matter and the forces that hold them together, a testament to the profound order within the seemingly chaotic quantum realm. These quantum theories also provide the definitive explanation for the very structure and stability of atoms, and by extension, the diversity of the chemical elements. In the classical view, electrons orbiting a nucleus should quickly spiral inward due to electromagnetic attraction, causing atoms to collapse. However, quantum mechanics reveals that electrons exist in discrete energy levels or orbitals around the nucleus. They can only occupy specific quantized energy states, much like steps on a ladder, rather than being able to exist at any arbitrary height. An electron can jump between these energy levels by absorbing or emitting a photon of a precise energy, but it cannot exist in between. This concept of quantized energy, first proposed by Niels Bohr and later refined by Erwin Schrödinger, elegantly explains why atoms are stable and why they emit and absorb light at specific wavelengths, giving each element its unique spectral fingerprint. The Pauli exclusion principle, which we touched upon earlier, further dictates that no two electrons in an atom can occupy the exact same quantum state, preventing all electrons from piling into the lowest energy level. This principle is fundamental to the formation of the periodic table, determining how electrons fill successive shells and, in turn, dictating the chemical properties of elements. It is the quantum rules that ultimately orchestrate the intricate dance of electrons, shaping the very architecture of matter and enabling the rich tapestry of chemistry that forms our world. Ultimately, the quantum world teaches us that reality is fundamentally probabilistic. While classical physics offered a deterministic view where every event is predetermined by prior conditions, quantum mechanics introduces an irreducible element of chance. We can calculate the probabilities of various outcomes for a quantum event, but we cannot predict with certainty which outcome will actually occur until a measurement is made. This probabilistic nature is not a reflection of our ignorance, but rather a deep, inherent feature of the universe at its most fundamental scale. It means that the future, in a very real sense, holds genuine openness, a myriad of possibilities waiting to coalesce into a definite reality. This can be a profound and liberating thought, reminding us that even in the grand cosmic scheme, there is room for novelty and emergent possibilities. As we drift into the quietness of the night, perhaps we can embrace this quantum truth, that our own lives too are an unfolding of probabilities, a unique and beautiful journey through a universe that is both governed by fundamental laws and imbued with an astonishing inherent freedom. Let this gentle understanding of the micro-world carry you deeper into a peaceful state of rest, knowing that the smallest scales of existence hold the grandest implications for everything we perceive. Our exploration of quantum mechanics has illuminated a universe far stranger and more intricate than our classical senses could ever suggest, a world of intertwined possibilities and fundamental uncertainties. We have seen how the Standard Model brilliantly describes the electromagnetic and strong nuclear forces, and how the Higgs field bestows mass upon particles. Yet, there remains a monumental, unfinished symphony in our understanding, the reconciliation of quantum mechanics with the force of gravity. While quantum theories excel at describing the very small, Albert Einstein's theory of general relativity reigns supreme in describing gravity and the large-scale structure of the cosmos, from planets to galaxies. These two pillars of modern physics, incredibly successful within their own domains, speak different mathematical languages and offer fundamentally different pictures of reality, especially when we consider extreme conditions such as the heart of a black hole or the very first moments of the Big Bang. The challenge lies in their core assumptions. General relativity views space-time as a smooth, flexible fabric that can be warped by mass and energy, creating gravity. Quantum mechanics, on the other hand, suggests that all forces, including gravity, should be mediated by discrete particles, gravitons in this case, and that space-time itself should be quantized, existing in tiny, indivisible packets, or quanta. This fundamental incompatibility leads to problems when physicists try to combine them. When the smooth, continuous geometry of space-time from general relativity is subjected to the probabilistic, fluctuating nature of quantum fields, the equations break down, yielding nonsensical infinities. It is as if we are trying to describe the ripples on a pond, quantum mechanics, with a theory designed only for the overall shape of the lake, general relativity, or vice versa. The scales at which these theories become relevant are vastly different, yet at the universe's most extreme points, they must converge. This quest for a theory of quantum gravity is perhaps the greatest challenge facing theoretical physics today, a silent call to uncover an even deeper, more unified truth about the universe. In response to this profound challenge, physicists have developed several theoretical frameworks, each attempting to bridge this divide, to weave gravity into the quantum tapestry. Two of the most prominent approaches are string theory and loop quantum gravity. String theory, a particularly elegant and ambitious framework, proposes that the fundamental constituents of the universe are not point-like particles, but rather tiny, one-dimensional vibrating strings, unimaginably small. Different vibrational patterns of these strings correspond to different particles, including the elusive graviton. This theory requires the existence of extra spatial dimensions beyond the three we perceive, curled up so tightly that they are currently undetectable. Loop quantum gravity, on the other hand, takes a different path, attempting to quantize space-time itself. It suggests that space-time is not a smooth continuum, but is instead composed of discrete, quantifiable loops, forming a fabric that is granular at the Planck scale, an incredibly tiny scale where our familiar notions of space and time are thought to break down. These theories, while still speculative and awaiting experimental verification, offer breathtaking visions of reality, hinting that the smooth, continuous universe we inhabit might be an illusion, an emergent property of a much more fundamental, discrete quantum structure. The implications of these ideas are truly profound, suggesting that space-time itself might not be a fundamental entity, but rather an emergent phenomenon. Just as the seemingly solid objects of our everyday world emerge from the probabilistic dance of quantum particles, so too might the smooth expanse of space and the relentless flow of time arise from a deeper, granular quantum substratum. Imagine looking at a photograph. From a distance, it appears as a continuous image, but zoom in close enough, and you reveal the discrete pixels that compose it. In a similar vein, the universe, at the most fundamental level, might be a network of quantum pixels of space-time, each carrying information about its geometry and connections. Our everyday experience of space as continuous and time as flowing smoothly would then be an approximation, valid at large scales, but breaking down at the smallest, most fundamental quantum limits. This perspective offers a serene, yet radical understanding that the very stage upon which the cosmic drama unfolds might itself be a participant in the quantum dance, constantly fluctuating and rearranging its scales far beyond our direct perception. This concept of emergent space-time also brings us to the Planck scale, a set of fundamental units derived from universal physical constants: the speed of light, Planck's constant, and the gravitational constant. At the Planck length, which is an unimaginably tiny 1.6 times 10 to the power of minus 35 meters, and the Planck time, an equally minuscule 5.4 times 10 to the power of minus 44 seconds, our current laws of physics begin to lose their meaning. This is where the quantum nature of gravity is expected to become dominant, where space-time itself is thought to become foamy and discontinuous. Below these scales, the very notions of where and when, as we understand them, may cease to apply. It is a boundary of human comprehension, a frontier where our current scientific tools and theories reach their limits. This ultimate fuzziness at the deepest level of reality can be a source of quiet contemplation, reminding us that the universe holds mysteries that transcend our immediate grasp, and that true understanding often lies beyond the veil of our everyday experience. Reflecting on these grand cosmic puzzles, on the quest to unify the very small with the very large, we can find a profound sense of our own place within this magnificent and mysterious unfolding. The knowledge that the space-time we navigate daily, the gravity that holds us to the Earth, might ultimately be an emergent property of a deeper quantum reality, invites us to view our existence with renewed awe. We are living, breathing configurations of quantum fields, experiencing an emergent classical reality, all while being part of a universe that is still revealing its most fundamental secrets. This ongoing journey of discovery, this gentle push against the boundaries of the known, is a testament to the enduring human spirit of inquiry. May these thoughts about the profound and elegant mysteries of the quantum world and our ceaseless quest to understand them bring a quiet sense of wonder and deepen your path towards a tranquil, restful sleep. The journey through the quantum realm has illuminated a universe of profound strangeness, where particles exist in states of superposition and are linked by entanglement, defying our classical intuitions. We've seen the intricate workings of quantum fields, giving rise to matter and forces, and the monumental quest to unify these microscopic laws with the cosmic grandeur of gravity. This ongoing search, particularly at the unimaginably tiny Planck scale, forces us to confront not just the limits of our theories, but perhaps the very nature of reality itself. If space-time is emergent, if particles are but ripples in fields, what then is the ultimate fabric of existence? This question leads us to ponder the role of information in the quantum universe, a concept that deepens the mystery and invites a quiet contemplation of what it means for anything to truly be. In the quantum world, information is not merely a collection of facts. It is a fundamental property, a conserved quantity. Unlike in classical physics, where information can be easily lost or destroyed, quantum mechanics suggests that information is never truly annihilated, only scrambled or transformed. This principle is famously highlighted by the black hole information paradox, a perplexing puzzle that arises when trying to reconcile quantum mechanics with general relativity. When matter falls into a black hole, it seems to vanish, taking all its quantum information with it. However, if information cannot be destroyed, then it must somehow be preserved, perhaps encoded on the event horizon, the black hole's boundary, or radiated away in a subtle form. While the exact resolution to this paradox remains a subject of intense research and debate, it underscores the profound importance of information in the quantum universe. It suggests that even the most extreme cosmic phenomena must adhere to the conservation of quantum information, implying a deeper, more resilient underlying order than we might initially perceive. This idea that information in its essence is eternal can bring a quiet sense of reassurance, like an echo of permanence within the ceaseless flow of change. It reshapes our understanding of what constitutes a fundamental building block of reality, moving beyond mere particles and forces to a realm where information itself plays a pivotal role, perhaps even as the ultimate substrate of all that exists. This brings us back to the enigmatic role of observation and the measurement problem, a concept that continues to challenge our intuitive grasp of reality. As we explored, a quantum system exists in a superposition of all possible states until it is measured, at which point it collapses into a single, definite outcome. This implies that the act of interacting with a system fundamentally influences its reality. It's not that we are simply passively observing an already fixed universe. Rather, our interactions, even at an unconscious level, play a role in defining the reality that emerges. This is a subtle yet profound distinction. The universe, at its deepest quantum level, is not a predetermined tapestry, but a canvas of potential, where the strokes are made through interaction. This shift from a purely objective, independent reality to one that is, in some sense, participatory, is one of the most radical departures from classical thought. It suggests a delicate interplay between observer and observed, a quiet dance of definition where possibilities condense into concrete events. To truly grasp this, one must let go of the ingrained notion of a fully formed, independent reality awaiting our discovery, and instead embrace a more fluid, interactive picture of existence. It is a profound invitation to consider our own role, however small, in the continuous unfolding of the cosmos. The ongoing scientific discourse surrounding the interpretations of quantum mechanics further highlights this deep philosophical challenge. The Copenhagen interpretation, perhaps the most widely accepted, emphasizes the probabilistic nature of quantum reality and the role of measurement in collapsing the wave function, without delving into what happens to the other possibilities. It suggests that asking what a particle is doing when not observed is simply not a meaningful question, posits branch outcome. In this view, all possibilities are realized, but in separate, inaccessible universes. Then there are other interpretations, like pilot wave theory, which suggests that particles always have definite positions but are guided by an invisible quantum wave, or objective collapse theories, which propose that wave functions collapse spontaneously without the need for an observer when a certain physical threshold is met. The very existence of these diverse yet equally valid interpretations reminds us that even at the forefront of scientific discovery, there is ample room for profound philosophical contemplation. It is a gentle invitation to explore the boundaries of what we consider knowable, fostering a sense of humble wonder at the universe's capacity for mystery, and encouraging a peaceful acceptance of the multifaceted nature of truth. These deeply strange quantum phenomena, while seemingly confined to the subatomic world, ultimately underpin the stability and existence of everything we experience. The very fact that atoms hold together, that chemical reactions occur, that light interacts with matter in predictable ways, all depend on these quantum rules. Our bodies, the air we breathe, the ground beneath our feet, are all intricate arrangements of quantum particles behaving according to these probabilistic laws. The delicate balance between the inherent uncertainty of the quantum realm and the emergent stability of the macroscopic world is what allows for complexity, for life, and for consciousness to arise. It is a testament to the universe's exquisite design that such a fluid and probabilistic foundation can give rise to the structured and seemingly solid reality we inhabit. This grand coherence, emerging from such fundamental strangeness, can inspire a deep sense of peace, a quiet appreciation for the hidden mechanisms that allow us to simply be. It suggests that even our most profound experiences, our thoughts, and our very awareness are intricate patterns woven from the quantum fabric, an astonishing dance of energy and information that continually shapes our perceived reality. And so, as we reflect on these profound quantum insights, we are reminded that our understanding of the universe is an ever-evolving journey, a continuous unfolding of deeper truths. The micro-world, far from being a simple miniature version of our everyday experience, reveals a reality that is fundamentally different, more dynamic, and more mysterious. It teaches us about the interconnectedness of all things, the inherent role of observation, and the probabilistic nature of existence itself. This knowledge, rather than being unsettling, can bring a quiet sense of expansion, an awareness that we are part of a cosmic dance far grander and more intricate than we often realize. In this deep contemplation, we can find a gentle release, allowing our minds to settle into a state of tranquil wonder, knowing that the universe, in all its quantum glory, holds us gently within its vast and truly profound sleep. This intricate dance has led us to ponder the very nature of information and the emergent quality of space-time itself, particularly at the unimaginably tiny Planck scale. Yet, even as we consider these grand, abstract concepts, it is important to remember that the quantum world is not just about distant black holes or theoretical strings. Its strange rules govern the very fabric of our immediate reality, influencing even the most seemingly mundane aspects of our existence, including the solidity of the ground beneath our feet and the touch of our own hands. One of the most surprising revelations from quantum mechanics is the profound emptiness within what we perceive as solid matter. Our everyday intuition tells us that a table, a book, or even our own bodies are dense, tangible things, full of stuff. But when we delve down to the atomic scale, this intuition completely breaks down. An atom, the fundamental building block of all matter, is actually almost entirely empty space. Its tiny, incredibly dense nucleus, composed of protons and neutrons, is surrounded by a cloud of electrons. The scale of this emptiness is truly staggering. If an atom's nucleus were the size of a small pea, placed at the center of a football stadium, the electron cloud would extend to the stadium's outermost walls. And everything in between would be nothing but vacuum. The electrons themselves are not tiny planets orbiting the nucleus. They exist as diffuse probability clouds, smeared out across this vast emptiness. So, when you hold an object in your hand, what you are fundamentally holding is mostly space, structured and held together by invisible forces and the peculiar rules of the quantum realm. This realization can be deeply calming, offering a new perspective on the illusion of solidity and the ephemeral nature of all physical forms. What then gives matter its apparent solidity? Why don't our hands pass right through a table, or why don't we fall through the floor? The answer lies in the electromagnetic force and a crucial quantum principle, the Pauli exclusion principle. At the atomic level, the outer layers of atoms are populated by electrons, which carry a negative electric charge. When two atoms come close to each other, their electron clouds strongly repel each other due to this like charge repulsion. This electromagnetic pushback is what we consciously perceive as the sensation of touch or solidity. There is no true contact in the classical sense, no merging of matter. Rather, it is a dance of repulsion, an invisible cushion of electric fields keeping atoms from overlapping. Furthermore, the Pauli exclusion principle, formulated by Wolfgang Pauli, states that no two identical quantum particles, particularly fermions like electrons, can occupy the exact same quantum state at the same time. This fundamental rule is not just a statistical oddity. It is a profound law built into the very fabric of the universe that dictates matter's structure. It is what prevents all electrons from collapsing into the lowest energy level around an atom, ensuring that atoms maintain their distinct shells and that different elements exhibit unique chemical properties. Without this principle, all matter would simply collapse into an undifferentiated, dense blob, and the complexity of the universe, including life itself, would be impossible. So, the solidity we feel is a direct consequence of these quantum rules, a testament to the elegant order emerging from the chaotic quantum dance. The very emptiness of space, even the vacuum between stars and galaxies, is also far from truly empty, as we've noted. It is a vibrant, restless sea of quantum fields, constantly giving rise to virtual particles that flicker into existence and vanish. This zero-point energy, or vacuum energy, suggests that the lowest possible energy state of space is not zero, but rather a teeming, dynamic realm of potential. This continuous effervescence of the quantum vacuum has profound implications, extending to the accelerating expansion of the universe itself, driven by what we call dark energy. While the precise connection between vacuum energy and dark energy is still one of the greatest unsolved puzzles in physics, the underlying idea is that the very void of space possesses an intrinsic energy that can exert a repulsive force, gently stretching the cosmos apart. This means that even the most seemingly empty regions of the universe are alive with activity, a constant, subtle hum of creation and annihilation that shapes the grand cosmic ballet. It is a quiet, powerful reminder that the universe is always in motion, always evolving, even in its deepest, most tranquil expanses. The intricate interplay of these quantum phenomena, wave-particle duality, superposition, entanglement, decoherence, the vacuum energy, and the fundamental forces, ultimately gives rise to the complex, diverse, and dynamic universe we inhabit. From the fusion reactions that power stars enabled by quantum tunneling to the intricate chemical bonds that form molecules and ultimately life, the quantum rules are the unseen architects of reality. Every atom in your body, every thought in your mind, every sensory experience is a manifestation of these deep, probabilistic processes. This profound interconnectedness, where the smallest ripples in quantum fields give rise to the grand structures of the cosmos, can evoke a deep sense of belonging. We are not mere spectators in this quantum universe. We are integral participants, woven from its very fabric, continuously engaged in its intricate dance. As we gently conclude our reflections on how the micro-world works, let us carry this sense of wonder and interconnectedness into the quietude of the night. The universe, at its smallest scales, is a place of ceaseless activity, profound mystery, and elegant laws, a realm where intuition gives way to the astonishing beauty of quantum reality. May the understanding of this intricate, probabilistic dance, from the emptiness within atoms to the vibrant energy of the vacuum, bring a deep and tranquil peace to your mind. fall asleep with the awareness that you are a complex, miraculous expression of these fundamental cosmic principles, a brief but brilliant pattern in the infinite tapestry of existence. Good night. As we consider the intricate patterns woven from the quantum fabric that compose our very being, a fascinating and highly speculative frontier of physics emerges: the realm of quantum biology. This nascent field explores whether quantum phenomena, typically thought to occur only in isolated, extremely cold or very small systems, might actually play a crucial role in the warm, noisy, and complex environment of living organisms. It challenges the long-held assumption that biological systems are too large and too messy for delicate quantum effects, like superposition and entanglement, to persist. Yet, evidence is slowly mounting that nature might have found ingenious ways to harness these quantum quirks for essential biological processes. Imagine for a moment the subtle whispers of quantum mechanics guiding the fundamental operations of life itself, a profound and elegant possibility that could redefine our understanding of biology. One of the most compelling examples comes from photosynthesis, the process by which plants convert sunlight into energy. Early stages of photosynthesis involve light-harvesting proteins that capture photons and efficiently transfer their energy to reaction centers. Research suggests that this energy transfer might be guided by quantum coherence, a state similar to superposition where energy can explore multiple pathways simultaneously, essentially finding the most efficient route through a complex molecular network. This quantum shortcut allows plants to achieve near-perfect efficiency, a feat that would be impossible if energy transfer relied solely on classical random diffusion. Another intriguing area is the navigation of migratory birds. Some theories propose that birds use Earth's magnetic field to orient themselves, and that this magnetic sense could involve quantum entanglement within specific molecules in their eyes. The entangled electrons in these molecules might react differently to subtle variations in the magnetic field, providing the birds with a quantum compass. These are not definitive proofs, but compelling hints that life, at its most fundamental level, might be leveraging the strange rules of the quantum world to its advantage, quietly operating at the very edge of what we understand about physics and biology. The potential for quantum effects to influence even higher-level biological functions, such as consciousness itself, remains a deeply controversial and highly speculative area. Some pioneering thinkers, like Roger Penrose and Stuart Hameroff, have proposed that consciousness might not be a purely classical emergent property of complex neural networks, but rather could involve quantum processes occurring within the microtubules of brain neurons. This orchestrated objective reduction theory suggests that consciousness arises from quantum coherence and its subsequent collapse, linking the subjective experience of awareness directly to the fundamental uncertainty of the quantum realm. While this idea is far from mainstream acceptance and faces significant scientific hurdles, it represents a bold attempt to bridge the explanatory gap between the physical brain and the phenomenon of consciousness, offering a vision where our very thoughts and perceptions are intricately woven into the quantum tapestry. It asks us to consider whether the subjective inner world we inhabit might be a direct reflection of the universe's most profound and subtle mechanics, inviting a deep personal contemplation of our own existence as a quantum phenomenon. The very act of observing, of forming a thought, might be a tiny echo of the universe's own quantum choices, a continuous process of reality solidifying from a sea of possibilities. Beyond biology, the practical applications of quantum mechanics continue to expand, reshaping our technological landscape in ways that were once considered science fiction. We've already mentioned quantum computing, but consider the everyday technologies that rely on these principles. Lasers, which power everything from fiber optic communication to medical surgery, operate by precisely controlling the quantum transitions of electrons within atoms. Semiconductor devices, the very heart of all modern electronics, from your smartphone to supercomputers, function because of our ability to manipulate the quantum behavior of electrons in materials. Magnetic resonance imaging, or MRI, a vital diagnostic tool in medicine, harnesses the quantum property of nuclear spin to create detailed images of the human body. These technologies, now commonplace, are powerful testaments to the predictive power and tangible reality of quantum mechanics. They demonstrate that even if the quantum world feels abstract or counterintuitive, its rules are rigorously applied and thoroughly understood enough to build the foundations of our modern world. It is a quiet miracle of engineering, transforming the elusive principles of the very small into tools that profoundly shape our daily lives, a harmonious blend of abstract theory and concrete utility. Yet, despite these incredible successes, the philosophical implications of quantum mechanics continue to provoke deep thought. The measurement problem, the question of when and how a quantum superposition collapses into a definite state, remains an area of active debate and interpretation. Some physicists lean towards the idea that the universe simply chooses an outcome when a measurement occurs, while others, following the many worlds interpretation, believe that all possible outcomes are realized in branching parallel universes. These interpretations are not mere academic curiosities. They challenge our most fundamental assumptions about the nature of reality, causality, and even the role of consciousness in the cosmos. There is no single, universally accepted answer, and perhaps there never will be one that fully satisfies our classical intuition. This ongoing mystery, this graceful ambiguity at the heart of existence, can be a source of profound peace rather than anxiety. It invites us to embrace the unknown, to find beauty in the questions that remain unanswered, and to accept that the universe is far richer in its possibilities than any single fixed reality could ever be. This grand tapestry of quantum phenomena, from the vibrating strings of theoretical physics to the quantum whispers within living cells, constantly reshapes our understanding of ourselves and our place in the cosmos. We are, quite literally, made of probabilities, existing in a reality that is both profoundly structured and inherently fluid. The gentle hum of virtual particles in the vacuum, the entangled dance of distant photons, and the subtle quantum coherence within our own biological processes are all part of the same magnificent, interconnected story. Embracing this perspective can bring a deep sense of calm, dissolving the rigid boundaries between self and universe, between observer and observed. It encourages us to see ourselves not as separate entities, but as an integral, active part of the universe's self-organizing quantum dance. The very act of perceiving, of contemplating these ideas, is a quantum process in itself, a moment where the vastness of the cosmos is reflected in the intricate workings of our own minds. This realization that our internal world mirrors the external quantum reality can be a source of profound serenity, a profound awareness of the seamless unity between the microcosm and the macrocosm. It is a reminder that even in the quietest moments, the universe is alive within us. May these deep thoughts about the intricate and wondrous world of quantum mechanics carry you into a realm of tranquil sleep. Remember that the universe, at its most fundamental level, is a place of profound mystery and elegant laws, a continuous dance of possibilities from which all reality, including your own, emerges. You are, in every atom and every interaction, a part of this astonishing quantum tapestry. Fall asleep with this feeling of serene wonder and an expanded understanding of the cosmos that cradles us all. Good night.